Check. Check 1 2.
Developer and a friend of mine.
Oh, good. Yeah. This is live.
Very nice, thank you. Even streaming?
Yeah, you're streaming now. And then as soon as he's ready to go, so switches and the maximum combination of 4 slides. I had a friend of mine who's an artist. He did EuroBSDCon and throughout. So they come, when they see it, they know. It's awesome.
Looks like we're good now.
Okay. Don't like those rough starts.
We also started late for the last talk. The keynote was a bit longer.
Yeah.
So that was a bit annoying, and you know that ate up the break.
Wait.
You.
Welcome back, everybody. Good to see you all here. Our next talk is going to be by Dr. Nicola Mingotti. I hope I'm pronouncing it correctly.
Yeah.
And we're going to talk about autonomous sensors, wind speed logging, and that sort of thing with NetBSD.
Yeah.
Please.
Thank you. So, hi everybody. This is my first time at the EuroBSDCon. I come to talk to you about GPIO in the Raspberry Pi and NetBSD. Our final application is to build a wind speed logger, but the main subject of the talk is GPIO. So, warning, this document didn't go any through peer review process, like let's say detailed peer review process, so double check what you see here before putting in your machineries, okay? So, a few words, who I am, what I do. I'm Dr. Nicola Mingotti. My PhD is in applied mathematics / statistics, and I have also a master in finance. But here we talk about computers, so the thing about computer I learned myself because I like them. Relevant experience, I was technologist at the National Institute of Physics in Florence. For a while I worked at Stanford's LAC as a research associate. And then I developed software for different companies. I have my own companies, but I mostly work for my family company. I'm a husband and father, and the little boy you see there is my son. So our company is this. I work there most of the time, and what we do is big plant for agricultural products. We have also machines. This is a sampler, for example. And we patent sometimes new stuff like this that is holding solar panel or silo. So if you want to see more, there is a link here. All links in my presentation are of this color. Okay, table of content. First of all, there is installation because first time, this time these slides are meant to be read. I wrote them in such a way that they are readable. So if you miss something, you can read it later, no problem. And first part is installation. That's completely different from PC installation. But I will not talk about it. It's written in detail what you have to do to have NetBSD running on a Raspberry Pi, okay? Then exclusion and limits, what I will not talk about. And then GPIO. GPIO, what they are, what do they do? How do we control them? For example, from the shell at the beginning and then in C. To go faster. Then a few related drivers that are very interesting, GPIO IRQ and GPIO PWM. All along, we will see application. I will leave you some exercises that I hope they are entertaining. And finally, we'll see how to build a wind speed logger with this built knowledge. So, I told you this is installation part. My objective is that you are right here. Good. First, we will go GPIO. Discussion what is GPIO and electrical properties. So self-imposed limits. Be careful. What I talk about here is only about Raspberry Pi 3B+, and only about NetBSD 10.0. I checked it on the GPIO or the pins is what is on the boot of NetBSD. You don't change. Then, on digital GPIO, for example, in some machine, there are AC converters. We don't talk about that. We go only about high or low. 0 voltage, 2.3 voltage. Okay? We work at secure level 1. What does it mean? So we don't have access to that memory. That is, we cannot toggle a pin state writing in a memory location directly. That would be cool, but we can't do it. No transistor and no IC. Why? To keep the circuits as simple as possible for people who are starting. Doing so, We are limited to 18 milliampere in output.
That would be
That's
cool,
very little.
but we
With
can't
this one,
do
you
it.
turn on a LED, but you can't.
No
run,
transistor
for
and no
example, a
IC.
relay.
Why? To keep
So
the
no
circuits
AC.
as simple
Then you
as
can't
possible
run
for
motors,
people who
no
start.
speaker, nothing. You do the best.
Doing so, we are limited to
Program
education
on
directly.
in output.
That
So
would be
that's very
cool,
little.
but we
With
can't
this one,
do
you
it.
turn on a LED. And
You
program on
no
just
transistor and no
for
IC.
relay.
Why? To keep
So
the
no
circuits
AC.
as simple
You
as
can
possible
run
for
mobile,
people who
then
start.
speaker, not to watch this. You do the best. Lua natively control GPIO, and it's very easy to do it. So watch the man page, here the link. Watch the man page, it's very easy to read. So again, generalized pin input and output is this GPIO. Where they are? They are here. They are these metal pins. When a GPIO is set as an output pin, it can be at tension 0 or at tension 3.3 volt. When it is an input pin, instead, the story is different. It is considered 0
Is this
for off,
GPIO?
for low.
Where they are?
If
They are
the
here.
tension is between
They are
0
these
volts
metal
and
pins.
1.8 volt. If
When a
tension is between
GPIO
1.8
is set
volt
as an
and
output
3 plus
pin,
3.3
it
volt,
can be at
then
tension
it's
0
considered
or at
state
tension
high.
3.3
Now,
volt.
big warning.
When it is
Don't
an input pin,
apply higher
instead, the story is
tension than
different.
3.3 volt
It is
to input
considered
pins because you're
0.
going to
Is
provide
this
off,
GPIO?
low.
Where they are? They are
Another
here.
tension just
They are
0
these
volt
metal
and
pins.
1.8 GPIO.
When a GPIO is set as an output pin,
3.3
it can
volt,
be at tension 0.
you can override this, but you're going to find problems. And also, GPIO has high impedance. That means that very little current goes in. There is not specific number on the internet, but they say nanoampere, so very little current goes in. How do we identify GPIO? So there are two ways. The hardware naming scheme, let's say, so 1, 2, 3, 4, 5, that's the logic thing you would think. But then when you talk to the operating system, you are going to use this name, GPIO 17, GPIO 27, and so on and so forth, okay? This is good to know, because in the operating system, you will use these names. We will use here in this presentation only what is boxed in the pink boxes, let's say. And then I recommend, if you are starting, don't use this GPIO that you see they have already mapped some function. Just use the one that they are free. It's better, it's easier. Okay, the basics. Configure the pin for input-output and set input or output state with GPIO-CTL. That is a command that you can run from the shell. Application, turn on and off a LED. Application true, read the switch. Circuits, basic circuits. If you want to work with electronic, you have to do circuits. This is the simplest output circuit that you can make. You have here your pin 9 is GND, that means ground, is the 0 volt, let's say. And pin 11, or GPIO 17, we are going to set it as an output pin. Therefore, this can be at tension 0 volt or 3.3 volt. If it's 0 volt, then there is no different potential between here and here, so nothing happens. If it's 3.3 volt instead, there is a current flowing here. How much current? 15 milliampere, because I put this resistor, that just not to break the limit of the 18 milliampere I told you before, okay? So be careful with resistor. It's ohm low, it's very easy. Anybody can do it. And the LED will turn on, of course, when it's current flowing around. And so you see the LED here is on, for example. This is the FreeSync. FreeSync is a software, it's good for who is starting. For people who is not familiar with this representation, okay, you can start with this one. But I strongly recommend you that you learn how to do this thing by hand before wiring the circuit, even in the breadboard. Very well, we prepared the circuit. Now we need to tell to NetBSD how to do the thing, okay? So first thing to do is to, in rc.conf, you write this, GPIO, yes. Second thing to do is, in gpio.conf, you say, okay, word, the device is dev GPIO 0, the one the device to whom you are talking to, let's say. So here you say, dear device GPIO 0, I want the pin 17, and be careful, this is GPIO 17 pin, okay, not pin number 17, okay? I wanted to set it as an output pin. And then in the second line you say, I want it to be at state 0 when you configure it, so off. Then you reboot, as I told you, that configuration become working only when you reboot. And you reboot, you check the list of available pins here, you see, GPIO-CTL, GPIO0 list, and it tells you, I know about GPIO17. Good. So now you can turn it on, off with this 0 and this 1, or toggle the state with the parameter 2. Toggle the state, change the state, whatever it is, turn it in the other way around, okay? This does turn on and turn off the LED. There is not anything complex to see. Let's see the reverse. Let's configure an input pin. Configuration. Pin 1, the 3.3 volt, let's go to see it maybe. Pin 1, which is 3.3 volt. And pin 13, that is mapped to GPIO 27. They are connected. There is these resistors that I put only to remember not to make short circuits if possible, okay? But it's not really necessary because no current will ever enter here since it has high impedance. But if it's for me, I recommend you put the resistor for no shorts. Okay. Then I tell you another thing. When we are going to configure this input pin, what I do by default is I set it as pull down. Pull down, simply saying it, is that when you read the pin and there is nothing connected to it, you will read 0, okay? If you don't do this, when you read the pin and you connect nothing, it's quite random what you could find, okay? So what you don't see in this configuration, because it's inside the Raspberry, is this resistor and this connection. So this circuit, when you say the pin is in pull down, is actually this circuit, okay? So there is this extra resistor, 50 kilo ohm, connected to ground. Therefore, what will happen now? Well, this is my switch. The switch is open. I read the pin state, no problem, because it's connected to ground, so the tension is 0. That's it. I close the switch, what happened? That the current flows from here to here to here, and these two resistors act as a voltage divider. Therefore, you will read 3.28 volt. Actually, you will see only on and off, but this is on, because between 1.8 volt and 3.3 volt, it's on, okay? Good, the switch is this thing, this little component you see here, freezing representation, there is the push button because I didn't find the switch. Configuration, as before, GPIO yes, and GPIO.conf, again, tell GPIO 27 is an input pin, in pull down, what I told you before, okay, pull down. Reboot, check the list of available pin with this, it tells you, I know about GPIO 27, okay, so read it with this command. You see it's like before, but there is no number here. And it tells you in standard output state 0, and in fact, the switch position is this one. Be careful because the exit code is 0. When I did it the first time, I thought the output was in the exit code. No, the output is in standard output. Then you turn the switch on, you go to read again, state 1. Okay, it works. We are able to read digital pins. Okay. Let's go to the next level. We ask ourselves, how fast can we be with GPIO-CTL? And the answer is here. Maximum 80 hertz, or if you want, 6 milliseconds per operation. It's not much. We are quite slow, okay? So let's try it in C. As everybody knows, you want something fast, you do it in C, no? So you do it in C with IO-CTL, and okay, let's say this. Usually when you change configuration fast of a pin, writing is called bit banging. When you read fast, it's called polling. These are two names. They are useful. So how fast can we be with IO-CTL? 160 kilohertz. So 2,000 times faster than before. Okay, that start to be interesting. Now we are fast enough that we can think in terms of square wave instead of in terms of on and off, on and off. No, square wave. And this will have a lot of application. But a word of warning here in this case. Be careful because here I'm treating my Raspberry as if it was an Arduino. That is, I'm going as fast as I can with a single process. But this is really unreliable because in Unix we have many processes running and somebody else could take time. And so, for example, your square wave will become slower, always stop for a while. So be careful what you're doing here because this is not really a way to do it, but it's good to understand. Okay, this is how I got those numbers. You can read it alone. I repeat 1,000 times the GPIO-CTL, and I see how much time it takes. That's it. That's how I found that number before, the 80 hertz, let's say. Write a pin state in C. Okay, this is mostly taken from this man page. There is nothing stellar here, and this is just a snippet for you to get started, okay? So you talk to the device dev GPIO, and then via IO-CTL, you say, GPIO write, I want to write to the pin, and you send this request structure. In the request structure, you write that the pin number you want to modify is 17, and the value you want to put is 1. The valuable values are 1 on, 0 off. That's it. If you change GPIO write with GPIO toggle, you get that toggle operation that I told you before. Just invert the state. It's useful sometimes. So you see, it's just a few lines. It's more include that code. And read the pin state, same thing exactly. In IO-CTL, you write GPIO read, and you get the result in the rec structure. And then you get it with GP value. That's it. How fast are we in C? I already told you about 160 kilohertz, and here is how I got it. I repeated like 10 million times the operation, and I took the time. That's it. Very simplistic. Okay. Let's go to more interesting things. From switches to square waves. So we say that we can turn a pin off, and you say here off, and now here it's on. It goes off again and on, and blah, blah. Okay, it repeats itself repeatedly. So we call period this distance between two rising signals. Okay, this is the period. This is called the duty cycle. That is the amount of time in the period that I'm on. Okay, and then there is, of course, the frequency in hertz is 1 over the period in second. It's just a few terms. Okay, with this concept, there are a lot of applications. Because, for example, the first big application is PWM, pulse width modulation. This is used everywhere, from speed of motors, dimming lights, whatever, servo motors angle. It's used in a lot of things. Because you see what you do is you change the width of the duty cycle, and this has two interpretations. You can give a different amount of energy out from 0 to a maximum that you say, or another interpretation from information point of view that you are spitting out a number between 0 and 1. Okay? Good. Another thing you can do is change the frequency of the thing. And this, what is the application of this? Of course, music. Of course, we don't do it here, any music, because we don't have the speaker. I mean, we don't produce enough current to make music. Instead, we will use these sparse pulses. Or sparse pulses, what are they? For example, I have in the company this meter that consumes how much energy is consumed, electrical energy. This meter is in the interface called S0. And what it does, it makes a pulse of 20 milliseconds, each 001 kilowatt hour consumed. Okay, so you see it makes something like this, bloop, bloop, every 001 kilowatt hour. So you want to, you know how much current you consumed, you count them. You count the pulses. This we will see more about this. Digital communication, of course, this you can imagine here that the frequency is fixed and you change the duty cycle from 0 to 1. And you use 0 to encode digital 0. You use 1 to encode digital 1. So this is the basic of digital communication. No? Okay. So status, what can we do now? We are able to control GPIO with GPIO-CTL. It's slow, but that is simple. We are able to go fast, but it's resource intensive. It's going to take all the CPU, and it's all quite unreliable. So what are the mitigation? Well, the Raspberry Pi has a PWM hardware, really, but we don't have the driver. And It has also interrupt support for the GPIO, but as far as I know, we don't have the driver. Possible mitigation that are NetBSD specific. We have GPIO PVM driver that make us look a GPIO pin generic look like a PVM. Though there are some hard limitation here because this TVN can do a minimum pulse of 10 milliseconds. So it goes to maximum frequency of 50 Hertz. That is very little again. Well, it's better than nothing. Then we have GPIO IRQ. Instead, this provides some kind of IRQ support to any GPIO pin. And we will see these two now, these two drivers. So you see, our objective now is to learn how to use them. And a couple of applications. We'll see only, I think, application 1 and 3 because of the time. The 1 second you can read alone. So GPIO PVM problem is not in the default kernel, so you need to recompile the kernel. I will not follow all the procedure here, it's long. But basically, you go to the generic, you add this line, you recompile, and that's it. You have GPIO PVM. Configure GPIO PVM. So we use this circuit as before. You remember the first circuit, no? With the LED and the resistor. And in GPIO conf, you write, okay, set the GPIO 17 as an output pin, and then you say to GPIO 0, attach the driver GPIO PVM to the pin GPIO 17 and attach only that pin to the driver. This is what that one stands for, okay? How you control it now? Well, you control it like this, GPIO PVM with sysctl. You need to say how long it will stay on, how long it will stay off. And the units here, that 50 that you see, is units, is ticks units, that in NetBSD, at least in Raspberry Pi, is 10 milliseconds. So, as I told you, 10 milliseconds is the minimum. So here what it does, 50 times 10, 500 milliseconds on, 500 milliseconds off. It is a blinky, okay? It is a blinky, half second on, half second off. Let's see it, just to see. The blinky, it's a classic. Can't miss. That's it, the blinky. Okay. GPIO IRQ. Okay, this is alternative to polling. As GPIO PVM is alternative to bit banging as fast as we can, as better as we can. GPIO IRQ is alternative to polling. That is to use a core to read as fast as you can a GPIO status. So luckily, GPIO IRQ is by default in the kernel, it is a module. So in rc.conf, you say modules yes, and then you load the module, GPIO IRQ, you see it here. You reboot, of course, you check, you load the modules. Then the output of this driver works like this. When you attach the driver GPIO IRQ, it creates this device file, device GPIO IRQ 0, and every time it finds an event, it writes in that file 3 bytes. The first byte is the device unit that for us is always GPIO 0. Then there is the pin number that if you are touching the pin GPIO 27, this number will be 27. State of the pin, this can be 0 or 1, as far as I read. Of course, if you are taking the state 0 or the state 1 you are interested in. But we will see more in detail in a minute. Allora, how do you read that GPIO IRQ 0? In the man page, there is an example in Perl. To be consistent, I have wrote the example in C, so we have everything in C. Okay, this is the simple program to read GPIO IRQ. It's very easy stuff. Okay. Okay, there is the classic push button, but I will not do it because it will take us too far. Let's see another application that is less problematic because it doesn't present the problem of bouncing. Okay, we connect 2 pins of the Raspberry Pi, one with the other. One is the input and one is the output, okay? In the input pin, we attach the driver GPIO IRQ. That is, as soon as you see a signal on, tell me. Okay? And the other pin, instead, we control it with GPIO CTL via the shell. So when we want to say change the state, okay? So the circuit is this. You see we connect GPIO 17, that is the output pin, you see it here. And GPIO 27, that is the input pin. with the famous resistor for avoid short circuit. That is completely not fundamental in this case. You can cut it if you want. There is this note here. So this is the configuration. As I told you before, this whole thing you already saw. Set the pin 17 as output pin, set it to state 0. Now the new thing, GPIO 27 is an input pin in pull down, okay, we know. And then GPIO 0, please attach the driver GPIO IRQ to the pin 27, only the pin 27, and this stands for catch only the rising edge of the square wave, okay? We catch only when it does like this. Not when it does like this, we don't care. We can only when it does like this. Reboot necessary. And now in this video, you will see in one terminal, I read GPIO IRQ 0, and in another terminal, I change the state. So here I read GPIO IRQ 0, start reading, you see it says nothing. Now I go on the other side. I toggle the state of the pin. He say from 0 I go to 1. And this, indeed, here he told us, change state. You see? And the only thing that they might be confusing, no, what is this? Is a strange number that you saw there. Let me tell what it is. Okay, you see 0 is because it's GPIO 0. 1B is the X representation of 27. Okay, so, and 1 is the rising edge. Okay, exercises I left you to do, which I think they are entertaining. Redo blinking using GPIO CTL instead of the shell script. It's very easy, of course. You say GPIO CTL toggle, and then sleep 0.5 seconds. Loop, basta, that's it. You will see surprises later about that so simple thing. All right. Exercise 2, dim a LED brightness in progressive step. As is illustrated here, this starts to be more complicated. So look at the LED and what is written on the shell. You see frequency 4 kilohertz, duty cycle 99. The LED is at its maximum. Duty cycle 50, 25. You see the LED brightness is going down. 10, 5, and that's it. 1. And then it loops, okay? So you can try to do that. So there are a few suggestions that I give you. Use 4 kilohertz or more to avoid the LED flickering, it's called. You will see the on and off, it's like that. Then problem, 4 kilohertz, you cannot do them with GPIO PWM because the maximum for GPIO PWM is 50 hertz. So you may think, I prefer, I do a GPIO toggle, or not GPIO toggle. I send on and off for different amount of time, and then I wait for a certain amount of time. There is a big problem here that, as you will discover reading this page, one page, you cannot sleep for less than 10 milliseconds in NetBSD, okay? So what I did here is actually I made empty for loops to lose time, empty for loops. So variation of the previous exercise that I called HAL 2001, that it is just the continuous version of before. Yeah, remember the movie? No, Dave. I don't know if you saw it. Okay. Okay, this is more a system manager thing. Suppose you want to disable a service with a switch, with a hardware switch, okay? I wish I could do sometime. For example, NTPD is one of my favorite. NTPD, I wish that to have a LED on my board that tell me when NTPD is on, and I wish to have a switch to toggle it on and off. Why? Because it makes a lot of output, especially when you are not connected to the network, and it makes a lot of pollution in the console, so it's annoying. It would be good. So this is the last exercise, let's say. Okay, at this point you know quite a lot about GPIO, and with a few components more, just a few, you can really build a lot of things with this thing, like open doors, like check temperatures, whatever. So how do I came to this thing and real-world application, that is the wind speed logger. So actually I learned all of this to build this thing that is installed above our company. So this is a wind speed logger specifics. Measures wind speed every 2 seconds, computes 1 minute and 5 minute averages, save data to a local DB every 5 minutes, accessible via HTTP, in the local LAN or via VPN via WireGuard, and it's powered via PoE. You see, in fact, there is only one cable coming here. It's the Ethernet PoE cable. So first thing to do is to find a sensor. I found this one. Documentation, of course, all in Chinese. And, in Chinese, there is written that when it does a complete turn, it makes 20 pulses. So you see isolated pulses. Is that example we have seen before? We need to count them. And also there is written that when it makes 20 pulses per second, it means that the wind speed is 1.75 meters per second, nothing more. So it implies linearity, whatever, it's like that. That's the documentation. So what we need to do, we need just to count this, and we know how to do it with GPIO IRQ. That is efficient. So you wire everything. The only thing that I will not cover here is that that sensor, unfortunately, doesn't work at 3 volts. It needs minimum 5 volts. So you need to make a very little circuits to use the 5 volts that come out of the board, because there is a pin with 5 volts, so you can use that actually. But you cannot enter into the GPIO with 5 volts, so you need to adapt a bit there. Then you make your, when you're sure that the thing works, you take your soldering iron and you solder everything. I recommend this if you are starting the solderable breadboard, because the traces are the same that you have in the breadboard, so you just copy what you did on the breadboard. And also this is very useful in the Raspberry and also in the BeagleBone, because they have these two headers where you can apply this circuit, you plug it on very well. Case is more difficult than what it seems to find a reasonable case, because you have a hat now. You have these circuits above, so you may need to do some modification. For example, you see this one, spacers I put. Finally, this goes outdoor, so you need to prepare the housing. This I bought at the hardware store, but there are a few problems. This machine needs to be ventilated. You cannot close it somewhere and that's it. So you need to make some holes, and then for the rain to enter, I printed these 2 gable vents, they are called. And that's it. The thing is completed. Now the services is the classic that you see everywhere, cron, HPD, and TPD. This one I recommend for this kind of machines, because MDNSD, because sometimes you take it from where it's installed, you put it near your computer, you want to test it, and at least you know it. If you do SSH, blah, blah, PF wind local, you will log there. You don't tend to worry about what will be now the IP of this. Yeah, okay. It's very useful. Then the classic, again, the classic, the wind speed service is the only little program that I wrote that collects data, go to read the GPIO IRQ, that I told you, that file, and makes it available in HTTP. And so the user, or let's say advanced user interface is this one. You call it with curl, or if you go with the web browser, and it answers you. In each case, answers JSON, but whatever. I didn't do the GUI because nobody, except me, nobody is using now, so it was useless. Okay, where to learn more and why BSD and NetBSD. So for me, one of the best books available on this subject is this one from Dr. Molloy. I have also the first edition of this. It's very good because it covers also the electronics part. The other thing is that all about Linux. and the big old board. So if you want to use different operating system or machine, you need to do some work. After that, you will need to read very carefully the man pages that contain a lot of information. A lot of information, very good. And then there are mailing lists when you don't know how to do it, and better you send an email before losing days and days. 10 minutes. Well, yeah, we make it. So if you are very new, of course, start on the social. Don't go and bother people on the mailing list. Reddit, Facebook, they are okay. Yeah. For the installation part, you can go there. I mean, okay, why BSD and not BSD? So the story is this. Usually, I built about 10 of these machines, and for different purposes. Usually, I keep the operating system that is inside the board, because that simplifies a lot everything. But recently, they have this good idea in Linux to delete sys/class GPIO. That is, they trashed all my script and all my programs about GPIO programming. That was very nice. So I looked for some alternative, a bit more stable, let's say. Why to remove something that works? And so I was familiar already with OpenBSD and FreeBSD, and I know that they are well documented and they change in a reasonable way, and documented mostly way also. I found the drive. I knew that I had to read a pin, so I knew that I wanted interrupt on the pin. And I found this driver in NetBSD, GPIO IRQ, and so I said, okay, I will try it in NetBSD. And for me, it was a new thing, actually. And what I noticed, coming from other operating systems, often in the documentation, you are encouraged to change things, like try to do this, recompile the kernel, do that. That's very nice. This usually you're not suggested to do that. And so also quite easy to cross-compile. And I would say the feeling is that like returning to what was Linux like 20 years ago, like it was all in your hand. Let's say you can change what you want. And with this, I think I've said it all. So if you want to ask me something, I will try to answer. Try. Actually, I don't remember by heart, let's say, but I checked also on the internet for people who want to do very high frequency stuff, like radio stuff. I think it's in terms of megahertz, but look it on the internet. Also because this is not very well documented. You need to look what they wrote on the forums. There is a Raspberry Pi forum, like equivalent of Stack Exchange. There is written. I found it there.
Have you tried recompiling the kernel to run at a higher hertz frequency, like kernel clock rate?
In the man page, I will point you to a man page. In the man page, there is written, don't change the tick amount of time until you really know the consequences of that. And so since I don't know the consequences, I didn't even try to do it. But yeah, and of course, we are limited to user space programming by choice. Otherwise, if we also, I don't know, I never tried to build modules and things like that. So I'm really not prepared at the moment to do that kind of programming. So actually, the why, I don't know. But I asked in the mailing list, because I was not able to find it in man pages, And somebody answered, no, there is no interrupt driver, there isn't. I don't remember the name, but I wrote recently in the R mailing list. And for the PVM, I think somebody told me something related to the speaker and the audio. I think there is some problem because it's related also to the audio. But this is the maximum I can say.
Do you know if there is documentation available for the Raspberry Pi hardware devices, which we could use to write drivers?
See,
How to use hardware?
yes, I have it in the links. Let me see, because in the links, when I say the maximum current or thing like that, I think I linked. No, these high impedance I think come from a forum because it's not documented. No, where there are the limitations? No, the link is gone. But strange. Wait, in the driver part, I think I linked the source. Here, as PVM driver. I think here we go. Let's see. Yeah, raspberrypi.com. Perfect. This is the official. Yeah, this is their official documentation thing. As far as I know, after that there is documentation of processor, but I didn't read it. You're welcome. I didn't understand.
Does this documentation give the device register layout, register map? Does it tell you all the hardware functions?
No, this I don't know. No, I don't know.
If you have the documentation or a reference driver, then we could help you to write a driver for this if you like in the kernel.
I wish I could, but my first objective would be to actually make work well I2C, E2C. Because that has problem in the detection, and to have I2C working would be even more important, I think. Because we
Help with kernel engineering, we can help.
okay. Okay, thank you.
Very cool. We're out of time. Thank you very much.
I think, okay, thank you.
Hello. Glad to be here to present today about the scheduling priorities and FreeBSD. Thank you for coming and attending this presentation. It's actually my first presentation to EuroBSDCon, so I thought I'll do a few slides about myself, but very quickly. I'm French. I've been in the IT sector for a long time. I love some kind of weird and old languages. I've do all kind of stuff, such as developing an architecture in different business sectors. And my involvement with the BSD community, actually with FreeBSD, up to now, it has been for a long time, actually, but not really in public. In public, it has only been for a few years. And actually now I'm working full-time on FreeBSD, as I am a FreeBSD Foundation contractor since last September, working on different topics. We're going to see that. So just to mention a few of the work I've been doing during the last year, which is not connected to that presentation. There are several things. Some are small tasks, other are more critical bug fixing, or rather reporting those bug fixes to different branches, but then trying to have some background work about the problems we have in different areas. And actually, I mentioned here UnionFS because as part of the contract with the FreeBSD Foundation, I'm supposed to work on UnionFS, on revamping it, so it has not really started. I've been, for now, reviewing batches of changes by other people, which are doing quite nice work, but it should normally start in a few while. So coming back to the topic today, the project goals for this project, which is a kind of background project, is to try to fix scheduling APIs bugs, to try to decouple the implementation and interfaces, because actually we had lots of duplication or code duplication, and actually not exact duplication. It's also to work on better POSIX compliance where we can, and extend the usefulness, because we have some quite powerful APIs that could be used for a number of tasks, and today there are some bugs or there are some difficulties in using them. So this presentation has an accompanying paper, which is, in fact, was done for the Asia BSD conference at the beginning of the year. So, and in this paper, you can find a description of the API, of the different APIs we have in FreeBSD, which are RT-Prio, which was the first one, and I should say the kind of native one, and then the POSIX one. So if you want to use these APIs or see how they work, I advise you to read that paper. I've put the URL at the end of the presentation. So I'm not here going to survey these APIs exhaustively. I've tried to focus on a few different points that I hope are interesting, because in this project there is also a lot of menial work, a lot of refactorings, and that's more or less boring stuff to present. So I'm trying to present, I hope, what should be the most interesting to you. So this talk will be, there are two parts. I'll just speak a little bit about the background of scheduling, with not too many details, because it can be a full talk on its own, and just explain a little bit what you can do with these interfaces. And then we'll see some of the changes I've been going through during this project. So let's start with the background. So scheduling, I assume that you know more or less what it is, but it's a very small summary. Actually, you have threads that you want to run. Some are in runnable state, and it's the business of the system, because it manages the hardware, to decide where you are going to put the different threads and execute them. And also for which duration, because you don't want some thread to starve the whole system. So at some point, you will decide that, okay, this thread has run enough. It has exhausted its quantum. So in this example, it's T2, for example. Then we will deschedule it to put something else on top. And to do that, actually, classical way of doing that is using multi-level queues or multi-level feedback queues. The multi-level queue, it's kind of queue like that. You have different priority levels. Let's say that here it's the most important priority, and here the smallest one. And you have several threads in those different queues, and you schedule them based on, you choose the one which has the highest priority. So here in this example, that would be T1. But, and that's the problem, is that that explains a little bit how it works in real time, because you have these different priorities, you assign one, but then that means that each time you have a thread in 0 priority, it is going to be executed, no matter what you have on the system aside from that. So that's why there was this refinement quite quickly for time-sharing processes. It's the feedback queue. And actually, the feedback is that if you're running too long at some priority, we are going to degrade your priority so that we can let the other threads run as well. So here, if T1 has exhausted its quantum, it's going to come back in the queue, but at some lower priority. So here, and so then we'll take T8. Let's say that T8 has ended. And next time that we execute T1, also we are going to move it to the right here. And at some point, we will be able to execute these 2 threads that are waiting there. That's really the archetypal mechanism to deal with thread scheduling, at least in the old days. And the BSDs have been based on that. So FreeBSD internal model is quite close to that. There are 3 selection policies. The real-time one, it's a multi-level queue. So that's, you assign fixed priorities. You choose the thread with highest one. It's a fixed system. Then you have the timeshare part. It's a feedback queue, as I just explained, although it leaves out lots of details. And the idle time is a multi-level queue as the real-time one, except that the threads there have less priority than timeshare. So there are basically, so what I've just presented is the internal model. But, especially in the old days, all the interfaces you get are quite close to that internal model. That's why I wanted to present it first. So for RT Prio, it's an interface that comes from HP UX, but which was modified for FreeBSD. Basically, at start, there was only one system call, RT Prio. And then some years later, we added another one for threads. It's very simple. You can set or retrieve attributes. And the settings you have access to, basically, you have 2 attributes there, the scheduling type and the priority within that class. So here I'm talking about functional classes. It's different than what I showed before. Before it was how the system selects internally the different threads. Here you are more saying, okay, I want that kind of behavior. So there are several possible types. In fact, I've put in red the current behavior, and then I have another slide with the new behavior or expected behavior after the changes. For example, if we take interrupt threads, fortunately, you cannot change their priority. It's kind of system critical. But if you try to get the setting, you'll get random values. And basically, it's an initialized memory read. So that's a bit annoying and has to be fixed. Here, we have a range, a fixed range, but there is a problem with it that we'll talk about later in the presentation. And for kernel threads, the system reports, okay, it's normal priority, which is not, actually, and priority 0 for all these threads. So what I would like to come to is to have, here it will stay implementation dependent, but at least we'll get real internal value. And for kernel threads, it will be the same with a dedicated class. So that's just for reporting. that part. And the second part, after, with less priority, I have time-sharing threads. Currently, the range here is implementation dependent. Actually has changed as of FreeBSD 14. And even worse, it's dynamic. That means that if you constantly request the current settings, you're going to get different values. So that's kind of very strange. And it's obviously, from an administrator point of view, you don't really understand what's going on and what you can do with that. And idle threads, it's a kind of mirror of real-time threads. So what I would like to do, and I explained that a little bit later, I would like to have a fixed range here. And these values, of course, are not random. They correspond to nice values, which is one of the possibilities. It's not the only one. And I would like to fix also the caveat I'm going to talk about for idle threads. So the POSIX interface now, it's very similar, but there are some differences. The priority levels are reversed, so if you have a higher number in your class, actually you have more priority, but in RT-Prio, it's the opposite. So you really have to be careful depending on which interface you're using. There is also, according to the standard, we should provide an absolute priority scale, which means that the different priorities you have per class, actually they are not per class, they are global, and they should be globally comparable. That is to say, for example, if I choose, if I have real-time process threads, let's say having the highest range in a byte, let's say between 200 and 256, that means that if I have time-sharing threads, they must have a range assigned that is lesser than this one. You cannot have different policies with the same values, at least in theory. That's what the standard mandates. And also there is some kind of caveat because actually process and thread scheduling settings are not the same, not necessarily the same, but I'm going to go back to that. The only thing that is really the same as the RT-Prio is that all priorities are positive. So that's the theory. And to check, I've done a simple reality check on that to see which properties are important to have for compatibility and which others are not really important. So the reverse priority levels, almost everybody complies. But HPUX, no, curiously. With non-negative priority numbers, it's also okay. We only have 2 outliers there. But then things get a little bit fuzzy because for absolute priority scale, actually, there are none of the open source current Unix systems that really abide by that for lots of reasons, mostly historical, I guess. And about the process thread scheduling settings, actually all these systems, we used in FreeBSD, we used to support the process contention scope, which means that the different threads in one process, they compete against each other to get CPU time, but then it's kind of a hierarchical model, and then the processes themselves will compete for CPU. But it has not been the case for a long time now in FreeBSD, since abandoning the M2N threading library, KAC and. I'm not sure, maybe around that time, I would say. So the trick is that according to the standard, now all these systems would support only system contention scope, but that means that according to the standard, that if you use the API that are targeted to processes and not threads, those targeted to processes, they are not supposed to have any effect. They shouldn't do anything. And in fact, no system complies, actually except OpenBSD because they don't implement that. But that's the only, all systems do not comply to that. They actually, because these APIs are quite useful, and it would be a waste not to use them, not to implement them in meaningful ways. But there are different implementations. So that was a quick tour about scheduling policies and the different APIs and what you can do with it. Yeah, I didn't describe exactly real time, but with the multi-level queue, I hope that's clear what these classes are doing. So some of the impacting changes, although some of them are still under question, I would say. Yeah, so I said that for the time-sharing threads, we have dynamic levels. That is, if I try to set, for example, the level for the shell here to 10, okay, this is the reporting I wrote. This is obtained through the POSIX API, and this is obtained to the RT prior API. So you see that there is a discrepancy that shouldn't be there, or at least it should be clear why there is a discrepancy. And then if you query that priority over time quite quickly, you see that, okay, quickly it's as if you didn't specify anything. So it's mostly as if that was ignored. Then you get 0, and then, which I noticed the first time by chance, if you repeat that invocation quite quickly, you'll begin to see numbers increasing, which was kind of strange at first. But after analysis, it comes from the fact that you're using more CPU time that is accounted to the shell. And so the scheduler is going to increase that priority because it's dynamic. And so you're getting these increase in numbers. So you'll see it's not really useful for administrators because you have a setting, it doesn't really work in any meaningful way. And even for reporting, it's great to have internal reporting, but it's mostly for developers, not really for administrators. So there were also other problems with that. The different levels are tied to internal priority levels. So this is something which is kind of an implementation detail. And we have these inconsistencies I just showed when you query the different interfaces. Although internally, in the end, the code is the same, or some routines are the same. So that's really weird. So I'd like to switch to fixed values. So which ones? Actually, there are several answers possible. The Linux answer is saying, okay, there is only one level. But it's not the full answer, because actually they have nice values per thread, because they modeled thread through processes, and nice values were initially per process. So that was my idea here. We use nice values because these at least have some kind of meaning, so fixed meaning that is not going to change across different versions, or then the meaning of each nice value also is not fixed, but at least it's something stable that the administrator could reason about. So we would need them per thread, contrary to what we're doing now. And then this raises a number of questions. Are we going to still be POSIX compliant? Well, we are not going to be compliant to absolute priority levels, because the big thing here is that if you read carefully the standard, I think the most probable interpretation is that these different levels, these are levels as in multi-level queue I showed at the beginning, which means that if you set some thread to a high value, then it's never going to run if there are threads with lower priority. And obviously, that's not what you want when you're doing time sharing. That's exactly the opposite. So that means that we'll probably give up on that. But as I showed, we wouldn't be the first ones, actually. And then we have to have a mapping to process nice value, because we have to maintain that invariant, which is mandated by the standard. And there are also interesting effects that we could have with existing applications. Actually, not many applications are using the POSIX API. I've done a quick survey. There are some which are using it, but I think it's under compile options, or even you have to use some special runtime options. You have Ruby, VLC, for example, Handbrake. These are the kind of software doing video, or usually doing video or audio, that we use them, and they are not using them properly. So anyway, this will require fixing, but it's a separate, would say separate project. Okay, so I wanted to talk a little bit very quickly about the scheduling privileges. So effectively, if you are able to run threads in the real-time class, these threads have more priority than the regular kernel threads. So you can easily deadlock a machine if you're running something which is an endless loop or taking too much resources. So obviously, this has to be controlled. So traditionally, that was reserved to root. In FreeBSD, we have this privilege API that can actually allow to grant several privileges to some users or to some processes through the Mac framework. So it's quite powerful. I'm not going to describe it here. But I'm just listing the list of scheduling privileges we have today. It's a bit strange, actually, because some of them you probably can figure out quite easily what they're doing, but some it's a bit difficult. And actually, some of them are not used at all in the code. They are just declared, but never checked. And some are checked in some code paths, some others in other ones, but they all end up in the same code in the end. So that means that you can bypass one if you have the other. So that's a security problem. So my goal is to get rid of these ones and to keep only the essential one. This is for real time. There is a special privilege for idle time priority because it was believed that you could deadlock your machine as well using idle priority stuff. For example, if your idle priority takes a resource, it doesn't have time to free it, and then you have lots of processes running that would like to access the same resource, so you could have a deadlock problem. Actually, I think that for lots of complicated reasons, today it's not possible if you don't tweak the Yule scheduler too much. I don't think it's possible that this can happen, but still it's historical. And for a more practical point of view, if you want to use them, for example, you would like to put some background compilation into idle time, currently, so you have to be root, or you can use Mac priority, which actually grants the proper privileges based on belonging to some Unix group. So it's kind of useful for if you're doing sound processing, or even for the real-time part. But for the idle time part, it's great for compilation, for example, or some background stuff that you don't really care about and don't want to disturb your other work. So I said in the first part that there was a caveat with real-time priorities. Now I'm going to explain what it is. So this is again from the standard. So we should have at least 32 priorities, and it's very clear in the standard that each level is different and has to be treated differently. So at first I was saying I didn't notice that there was a problem because we have this constant, and I added some more checks about that to be sure that we're not going to reduce it. So everything seemed okay, superficially. But in fact, there is a problem, because we are doing internally priority levels conflation. So we have the FreeBSD run queue. The run queue is the essential brick to actually implement the multi-level queue and the multi-level feedback queue I just talked about at the beginning. But the trick is that it only has 64 different levels, although you have internally, we have 256 different levels, priority levels. So obviously you have to have some mapping, and the mapping is very simple. But that means that effectively for internal priorities, if you have 4 of them that are going into the same bucket. And all threads on the single queue are treated the same. It's basically what I showed in the drawings at the beginning. And to add to that, what we are doing is that for the different levels of RTP prior real time, so this is what the user sees, actually, the interface, each level is mapped one-to-one to some internal priorities, to some reduced range, obviously, but one-to-one. So effectively, you get that 4 consecutive levels are mapped to the same queue and are treated the same. So we are not compliant. So there are, again, several ways to fix that. I tried more, I wouldn't say it's a moonshot, but I just didn't want to try to fiddle with all the internal mappings we were doing. I had enough of that, so I decided, okay, we should just use a big run queue, which corresponds one-to-one with the internal priorities we have. And it solves that problem, but actually introduced another one.
So you have to scale how far back into the queue you reinsert?
Yeah, in fact, I will explain. So Yule is the default scheduler and has been in FreeBSD for more than 15 years, I would say. So what I said before is not exactly true. It's true for the old scheduler, for BSD. But for Yule, we have 3 run queues, actually. We had three run queues. And there were 1 run queue per selection policy. So as I showed at the beginning, real-time, time-sharing selection policy, and idle time. I hope you, there are lots of different terms that are almost the same. I hope you're not completely lost about that. Here, I'm really talking about how the systems internally choose the next thread to run. Because as I said, in the real-time policy, you have real-time threads, user-land real-time threads, but you also have kernel threads and interactive threads for Yule. So the time-sharing threads, they are divided into 2 classes by Yule. The first one goes into the real-time selection policy, and but after kernel threads, contrary to real-time user threads. And we have the batch ones, so they are not deemed interactive, and only these ones go into the time-sharing selection policy. So internally, we have a range of 88 priority values, but since we have a dedicated run queue for it, that means that we only have 64 levels. So we have to do some mapping. And computation is based, the computation of the priority value is done by the scheduler and is based on the CPU usage and the nice part, the nice value part. But if you're doing that and you just keep the usual selection, that is to say you take the thread in the queue that has the lowest value, corresponding to the priority with lowest integer value, then you're going to have all the usual problems and you're not really doing time sharing. So in order to circumvent that, you'll use NQ and DQ offsets. So we are not going in the run queue, we are not going to insert, for example, a thread with priority 0 in that range, so 136. We are not going to map it to the level 0 anytime. This is going to change, actually. And this is what is called the calendar queue. This is a mechanism to prevent starvation. Really, the real reason for doing that is trying to keep the 4BSD's decay, priority decays we have for fairness, and to have that, but stay big O1 in the number of threads. So instead of working the whole list of threads and changing their priority one-to-one, because that can cost a lot, instead of that, you're just changing the reference point. That's basically the idea behind the calendar queue. I've got a few drawings just to show how it works. So let's assume for a moment that it's only the time-sharing queue here. And we have 2 heads, the DQ and NQ head. And as usual, the highest priority is on the left with lowest integers. So at each tick, we move the NQ head. But the two heads are in lockstep. That is to say, the NQ head cannot move too far from the DQ head. Actually, initially, it was only one gap maximum. So this corresponds to time passing. And then let's say that we were running some T2 threads, and now the scheduler determines that based on the CPU ratio, it has a priority of 2. We are not going to, and here we also assume for simplicity that there is a one-to-one mapping. So if I have priority 2, I should go normally to queue number 2. But I'm not going to go into queue number 2. I'm going to actually go into queue number 3 because I have this offset. The enqueue head works as an offset. So I'll get here. And since the DQ head is still there, the starting point is here, so we consider that this queue has the threads with highest priority. So we are going to dequeue these ones and execute them. And once it's done, when the queue is completely empty, I can actually move the dequeue head towards the enqueue head, allowing the enqueue head to move again. And what's the effect of that is that, for example, now, let's say that the thread we were running, which could be T8, for example, creates a new thread that has priority 4. And then I'm going to enqueue that thread here in 6, because now my head is here at 2. So what happens is that, so T2, I will execute T2. But, oh, sorry, there are some drawings missing maybe. But that means that T4 will be executed after T10 and T17, for example. And we can assume that these were inserted with priority 5 when the enqueue head was at 0. So basically, that means that, OK, that thread has a higher priority, but in the end, we will execute it after these ones, just because time has passed. And this is the way we actually implement the anti-starvation mechanism. And this mechanism is quite sensitive to the timing, because you only move the enqueue head based on time, on ticks, actually. So with all the changes I talked about, now we have only one run queue. It's kind of implementation detail. But what has changed is that we have more values in the time sharing range now for a variety of reasons, because, for example, Jeff, the initial author of EULA, wanted more time sharing levels. And actually, we were able to free some because we are not conflating them anymore. So there were some kind of tricks in the kernel saying, OK, for this kernel thread, I want this priority. And for this other, I want this +4, just to avoid the conflation I mentioned. So now we have a lot more values. So we could have kept exactly the same number of values. But I wanted to experiment with using the full range. And the trick is that if we want to preserve the exact anti-starvation mechanism we have now, we actually have to preserve several things. We have to preserve actually two things. First, the ratio of contribution between the NICE contribution and the CPU usage contribution that are used to compute the actual priority by the scheduler. We have to preserve that. If not, that means that the NICE values are going to have different effects. And for starvation, we must also ensure that we are going to have the same span in the same amount of time. So that means that initially, we had to return to the same position after 64 ticks, because there were only 64 queues in the run queue, dedicated run queue. Here, we have a variable number of queue, which is configurable, by the way, now. And to regain that property, actually, we can have, it's approximate, it's really close. So we decided to change the rate of advances to the head. And the result of that is that if we test two threads with different NICE values on the same CPU, and we compare the CPU usage of the highest priority thread for the two different, for before and after the changes, then we see that we are able to approximately preserve the existing behavior. Whoa. And so we approximately preserve it, which was a problem with the initial series of patch. I've been discussing a lot with Jeff about what we should do next for EULA, but we didn't want to conflate that with some other changes. And wanted to have things separate because it's already quite a big change. So we seem to be good on that front. And then, unfortunately, it seems to be kind of usual in this project. You change something here, and then it changes something else, and then something else, and then something else. But there, it's not exactly the same case. I just noticed this. So if you have two different processes, two threads, one with minus 20, or with corresponding process having nice value of minus 20, it will only get 67% of the CPU, which is quite astonishing because it's the whole range of nice values here. So Jeff was not really aware of that problem. And so that's, it seems that we have other things to fix and to work on. So that will be continued. So, okay, I'm doing quickly because it's kind of a big project with big changes. Not everything, as I said, is really interesting to present, but there are several stuff. Actually, I've also tried to have all these changes in the Linux later as well, so there will be fixes in this area as well. So the work I have in progress is changing the priority levels for a time sharing part, at least for the RT prior interface. I'm just wondering if it's a good idea to do that for POSIX for some of the reasons I explained. We are not going to be compliant. We are already not really in this area, so is it really a problem? I think it depends mostly on how the different applications use that and if there are impacts or not. I don't think there will be, but this has to be tested with experiments and other tests. I would like also to allow some kernel threads to run in the time sharing selection policy, especially for the ones that consume a lot of CPU, because that can cause lags and jitter. I have observed that on several boxes with Jelly, for example. And although it seems, if you look at the code, it seems that it's the case already, it's not. If you analyze it correctly, you'll see that, in fact, it's not the case. I would like to have some better priority reporting as well, probably in PS and top. Probably this is going to be controversial or not, I don't know, because I think that showing the internal priority does not have much value for the administrator. It can be discussed, but because you can compare them for sure, but the raw value, you don't really know what it means. So I'm not completely sure about doing that or not. I would like to adopt, it's kind of easy, or not that easy internally, but to adopt scat batch from Linux, which is saying, okay, I have something in time sharing, but I don't want it to be interactive, even if the scheduler has the impression based on behavior that it should be interactive, but no, it's not. It's something that should stay in the background, more or less. And I would like to fix the nice values effect. So we are discussing with Jeff about how to do that without too much disruptions, although I'm not sure it's actually possible, but we'll see. Some code status. There are currently two big series of patches. There is one, so the 256Q, which seems to be nearing completion after the recovering the anti-starvation behavior. We will see with Jeff, but I hope that this one can be committed quite soon. This one is still more a work in progress because there are lots of plumbing stuff to change, so it's really a long part. But I would like to have all this in FreeBSD 15, or by then, having had reviews, comments. Maybe there are some things that I presented that won't make it because people really don't want that. It's not completely, there are things that seem to be quite open still. And some possible future work, hybrid scheduling, because we have that in CPUs on new laptops. It's a complex, really a complex topic, but probably we can have some simple policies to start with that could be effective. Other schedulers, because ULE was based on several assumptions, such as we will have so many threads that we cannot be dependent on the number of threads to select some next thread to run. In practice, it proved not really completely true. And actually, in Linux, the last two schedulers are not big O1. They are in log n, so, and it doesn't seem to matter much. And this could maybe enable some flexibility because the current mechanisms, they are quite rigid. There are a few parameters, but they interact in sometimes very strange ways. So maybe we should explore some alternatives there. I would like also to have some per process priority limit. This requirement comes from guys doing audio stuff on FreeBSD. It would be nice to have, and maybe some process mitigations, so some runaway processes mitigations when you have something in real time that goes completely mad. But we'll see. That would be more of nice to have, and there are already lots of things to do. So, okay, so it seems it's the end, and I've put there all the different URLs that could be of interest. I will post the slide just after the conference so that you can actually click on the links. This is the paper is on papers.freebsd.org. If you don't know that site, it's really nice because you can find all the papers of all the past conferences and the different code stuff that you can find. And I think that's all. And I welcome your feedback and questions, and now or later, because it's kind of complex subject. So there are things that maybe you'll figure out later and want to talk about later. So anyway, I'm available.
I'm interested in actual hard real-time applications with FreeBSD. Is there any roadmap towards that? Like, I think the story is we can't preempt system calls.
Yeah. No, hard real-time, yeah. At
Like
least to my knowledge.
Linux's preempt RT or something.
Yeah, it has never been on the roadmap, to my knowledge. But hard real-time, no. Soft real-time, yes, but.
So what's then the main use case for RT Prio?
Oh, for RT Prio, it's mostly when you want to do live sound or video processing.
Yeah.
That's basically all the use case we have.
Higher priorities, basically.
Sorry?
You need a bit higher priorities.
Yeah, or you prefer because
Over.
Exactly.
Yeah.
And I'll only press start when I announced you, so
Yeah.
anytime until your turn.
No worries.
have Dave telling us building a modern packet radio network with open source software, which I know nothing about, so I'll happily pass on. Welcome, Dave.
Perfect. Good afternoon. Yes, I'm going to talk about building a packet radio network in the current year using old technology. So for a bit of background, I'm Hibby, known as MM0RFN in the amateur radio world. I am unfortunately, first and foremost, a Debian developer, so that means that most of my solutions come from an insane Linux point of view. I'm a packet radio enthusiast. I like sending slow data all around the world. And I got a start in amateur radio in 2007, having heard about packet radio from a podcast called Hack 5 in the year 2006. I started my time in Debian and getting serious about open software in 2015, just fixing bugs, starting doing one or two things, and got slowly more sucked in. But I found myself drawn towards BSDs. I'm quite excited by them in general. And because of my excitement for amateur radio, I am a career radio engineer. I spend my time in a day job doing communication safety systems for the energy industry. So a quick summary of what we're going to go over. I'm going to do a brief introduction to amateur radio because not everyone is familiar with it, and I will arm you with some very helpful technical knowledge. I'll give you an introduction into what is now the UK and Ireland packet radio network, and then tell you how to get involved as well and what we're looking at next. And throughout, I'm going to have helpful graphics like this. They come from the Northeast Digital Association's 1994 annual, which is contemporary with the bulk of the technology that we're using. It's really not come on very far. So amateur radio is an old hacker hobby. It's been around for 100, 120 years. It really is a license to experiment on the radio frequency spectrum. Amateurs have access to a huge chunk of radio, all the way from long wave, 135 kilohertz is the bottom of the UK allocation, up to impossibly high frequencies, 250 gigahertz is the top end. The most attainable bands for everyone is 1.8 meg to 2.4 gig, with 10 gigahertz becoming more achievable as commercial hardware makes it cheap. The most common bands that you'll see are 144 meg and 430 meg. These are the common walkie-talkie bands, and they're just quite a nice size. You have to have a license to get on the air. Most jurisdictions have reasonable licensing these days. In the UK, we have a 3-tier system. Foundation is a barrier to entry that isn't very high to cross. In Ireland, it's a bit more difficult. There's a Class A and a Class B license. The only real difference is that you can do Morse code. Most other places have got rid of Morse code at this point in time. And everything that happens in amateur radio happens in the clear. There is no encryption. So we have a predisposition in the hobby towards experimentation and sharing. And it also stops corporate heavyweights coming in and stealing our band space. It's a hobby with a diverse range of sub-activities, and each one further subdivides. The same as software. You get a bit interested in networking, and then you get a bit interested in TCP, and then you get a bit interested in something else. You just keep going down and down and down. My preferred sub-activity that I do is create an ultra-lightweight portable station, climb to the top of a mountain, and speak to strangers in different continents from the top of that mountain. There's people who do amateur television, so it's not just talking to each other. So they're experimenting at the moment with DVB and DVB-S. There's experiments in DVB-T, which is multi-carrier, and that's quite exciting. There's a bunch of people who launch satellites, amateur satellites, and they've been going on since the 1960s. In 1961, Oscar 1 was launched. That's 4 years after Sputnik. So radio amateurs have been trying to do impossible things on shoestring budgets for a long time. And the other one that I'm excited about, Packet, is what I'll talk about today. Theoretically, it's a technical hobby. You have to know about radios, but it doesn't have to be. And there are people who just sit in their front room and speak to each other on a radio. And during COVID, that was a lifesaver for some folk. It's relatively easy to get started, as I say, with licensing. And overall, it is a bit ridiculous. This is me trying to talk to someone 10 miles away. I'd spent the afternoon talking to people much, much further away, but he couldn't be bothered getting out of his front room. So I had to wander around the top of a hill with 6 meters of carbon fiber above my head. Packet radio. Well, packet radio is a niche within amateur radio. And it is just Wi-Fi from long before the IEEE came up with the 802.11 working group. It's real slow networking over commercial hardware that we can buy off the shelf. We're all given call signs when we get our amateur radio licenses, and they form your addressing. It often gets confusing when you have a MAC address that is a call sign and an address for a layer above that that is a call sign, and a port might be a different call sign. So you can have very conflicting and terrible addressing schemes. It's all derived from X25, so that should give you an idea of how old it is. And there really are a limited number of applications that are common. Messaging and location tracking. The top picture is me driving home a couple of weeks ago. You can see where the big straight lines are, where the coverage gaps are. We use BBSs. BBSs are still cool. Don't stop doing BBSs. And file transfer through BBSs as well. And we're moving into general data transport as well. But that's still quite a niche part of packet radio. It is contemporary with early IP. Some people have called it a more elegant weapon from a more civilized age. And a lot of the state-of-the-art started out as homemade EPROMs that were passed around by friendly hams for Z80-based hardware. And this advert from page 76 of the Northeast Digital Association's annual is someone who wants to share his code either as a diskette or a ROM. And you can send him a message on his BBS 30 years ago, or you can turn up at his house and ask for it. The first documented experiments in packet radio were in Canada in 1978, and it's really grown arms and legs since then, and then the internet came along and it kind of fell away. Everyone got bored of slow networking. But it's still good fun. You can get BBS bulletins. You will absolutely not regret getting another 5 to 10 messages a day that mean absolutely nothing. I don't get many personal messages, but I do get this list every day. Arch Linux updates, Linux Today. If we look at this one, this is the Linux Today bulletin. You can see at the top all of the hops it's taken to get to me. It starts off at the bottom, LU9DC, who's in Argentina, and it works its way through the US, over to the Netherlands, back to the US for no reason whatsoever, and then ends up in Scotland. And this is just an excerpt of the Linux Today headlines. It is just the headlines and the leader text. There is no link to go to the website. You cannot learn more. You just get, there is a post on Linux Today. Should you like to read more? It's great. I love this crap. It's helpful to know as we go forward that when I talk about packet radio in the UK network, we're really dealing with 3 categories of link. We have our low-speed links, which are 300 bauds. That is characters per second. Sometimes we can do more than 1 character per second, so it might be 300, 600, 1200 bits per second, but it's always about 300 baud. We have a medium speed link, which starts at 1200 baud, and then a high speed link that is rocket fast at 9600 or faster. The low speed links are typically on the HF bands, that's 1 to 30 megahertz. It's really narrow bandwidth, and it's a really big size bit of equipment. This is my smallest HF antenna, and it really does just keep going and keep going and keep going. It's about 5 meters long, but I've been known to climb hills with antennas that are 30 meters, if not longer. In our mid-speed bands, that's VHF, 50 to 145 megahertz, so around about where you'd find marine traffic and air traffic. It's mid-bandwidth, and it's mid-sized equipment. The antennas are much more convenient. This one is only half a meter long, and it's lightweight and cheap. And then in the UHF bands, where we get to high speed, because we have lots of bandwidth to play with, the antennas get real small, and it becomes easier to make directed antennas. You move into dishes and microwaves and other fun technology. Of our links, the low-speed ones are intercontinental, and what we do is take advantage of physics in the Earth's ionosphere. So the HF bands are largely controlled by the sun. We pray to the gods of the sun that everything goes well. The sun has what's called the solar cycle. It's an 11-year cycle of activity. At the moment, we're approaching the high point, the maximum of the solar cycle, which is why we're seeing lots of aurora and lots of atmospheric effects. And what we do is we take our signal and shout it out into the ether and hope that it reflects off the very top of the ionosphere and comes down somewhere else 1,000 miles away. If the sun is particularly angry and it has released a lot of X-rays and particles, then this thing at the bottom, the D region, will get quite absorby, and it will stop the signal going through it, and you can't hear anyone. And it impacts satellite communication and other things, but it really cuts off our slow-speed backbone links that we're proud of. The medium-speed links are local area. They kind of reflect around a city quite nicely. You can do it from a car. You can do it from a hill. You get a good 50, 60 miles, 100 kilometers of range. And in the high-speed links, they're really just line of sight, point to point. So you're creating a backbone effectively. But as a packet radio fan, you control the full stack. You have every element of the hardware, and every element of the software is up to you what you choose to do. In 1994, it looked a bit like this. You had a big white stick at the top of your house, and that was your local link. And then you had a radio below that. You had a thing below that called a TNC, which is roughly equivalent to a network operating system device, and it also contains your modem. And then you had a dumb computer at the bottom. And computers are still dumb, but they're now a lot more powerful. The radio, you just change out for different bands. The antenna, you change out for different bands. So this is one of my high-frequency radios. It's quite small and compact. It only does 20 watts out, so it doesn't go that far. But I do take it up hills, so it's not too bad. It's not very OSI. It's from a time before the OSI 7-layer model was invented. So yeah, things clash and the schemes don't work, and layer 2 has a full connection model in it that asks for retransmissions instead of layer 4, and it's not the best, but it works. And yeah, you can change every bit of the stack, and as time has gone on, I say as time has gone on, from 1978 to 1994, things became software. So the TNC is now software. That's just a node stack that's on a computer. There's a few different implementations of that. The modem is now just software because computers can make noise. And we're not making a lot of sound, and we're not making it very quickly, so we'll just make things come out the sound card. The radio, well, software-defined radio is now a thing. And you essentially get a rack mount unit that can pretend to be a radio on the network, and it makes it much easier to go on strange bands. Cables can get quite expensive. The cable that connects your transceiver to your antenna is a great way to spend money in the classic audiophile style. Sadly, while your antenna can be many things, it cannot be made into software. We can control them with software, but we cannot make the antenna software yet. And computers can now be tiny. We've got Raspberry Pi 2, 0Ws, and all kinds of stuff. They get smaller and smaller and smaller. So we've taken this idea and told a whole load of people about it and started the UK and Ireland Packet Radio Network. And this is a map of what it looks like at some point throughout the day. All the small pins are different stations of different classes, yellow and green. And the one in the top left there has a couple of long-distance, slow shortwave links that are coming down here to England to send bulletins and emails and nonsense back and forth. It is inherently a social network because to peer with someone else locally, you have to speak to them and tell them that you want to connect to their radio. It doesn't just happen automatically. We haven't really invented routing protocols yet. But yeah, each bubble of these is a local area of people who've spoken to each other and started a mid-speed or high-speed network. And down here in England, they've spoken a lot and they've done quite well. And up in the northeast of Scotland, where I am, there's 4 guys, and sometimes we all fall out. There's a mix of experienced people who've been doing this for 30 years, if not longer, and there's new people who've only had their license for 2-3 weeks because they heard about it and thought it was cool. And there's a real mix of technical ability as well. Some of our operators and people struggle with the concept of mailing lists, and mailing lists can be quite difficult, but sending a new email with a new subject every time you want to reply to someone's question is a bit frustrating. But we do follow the tradition of what's gone before. On our layer 1, we have FSK. We have something that makes noises. On our layer 2, we use a protocol called AX25, and increasingly these days, we use something called IL2P, inspiringly named the Improved Layer 2 Protocol. It has such great features as checksums and forward error correction. We're really pushing the boat out. And on layer 3, we have NetROM. And as its name suggests, it was distributed as a ROM for networking quite some time ago. NetROM is a bit like Marco Polo. Your station announces its presence and says, I'm here. And everyone else says, that's great. I can hear all of these stations. And you build a routing table, and you can begin to move around the network. That only works locally. AX25 has a maximum packet length of 256 bytes. NetROM is an overhead of 20 bytes in that window, so that reduces our payload to 236 bytes. And on a link where you're sending 300 bits a second, that is a measurable amount of time. So we don't do NetROM on the HF links. We just know that we're going there, and we've set up our peering agreements in advance. This is the network in a different day. You can see the sun's a bit happier today because now my station in Aberdeen can also talk to England. Sometimes I'm grumpy with the English, sometimes the station's grumpy with the English as well. So we've made our network around a thing called a Nino TNC, which is a modem that's been made by a guy in the US, and it is a modern solder-at-home kit that is still under active development. And someone down in England, a guy called Tom, M0LTE, organized a group buy of boards through a Discord server that a lot of people were in back in November 2022. And we started supplying these things. The map didn't look like this in day one. We started off with 10 people wanting one, then 20, and all of a sudden we had 100 orders. And now we've shipped a couple of hundred of these things around the UK, and people have got really excited. Having the gear is great. Like, what's next? Now that I've got this and I can make my radio sing, does anyone else hear it? And the challenge of packet radio, once you've got all the gear, is that it's an overwhelming collection of information from 30 years ago, targeting mostly DOS, fragmented across some truly terrible-looking websites. And the state of the art is not in a good state. Like, we're using 30-year-old software, or software that's been in development by an amateur for 30 years. And we have bugs all over the place, and this was never meant to compile with GCC 14 or GC wherever we are now, and it's not meant to build to these standards. And I spend so much time patching terrible software. And it's a weird mix of closed source software and open source software, and there's a load of gatekeepers in there as well, just to make everything fun. And as I suggested at the start, there's just weird dead messages bouncing around all the BBSs, taking up airspace. Like, the state of the art isn't great. But to at least get involved, you have to find some local friends. If my radio can shout, someone has to shout back at some point. And if you're just shouting into the void, like as cathartic as it is, it's not very helpful. So we discovered that you could link systems together using the internet protocol. We could encapsulate AX25 over IP and then shoot it off to someone else's station over a VPN. So we built a virtual packet radio network where we could talk to each other using all the right technology, but over WireGuard. And that was good, and we've slowly replaced those long-distance links with the shortwave links as we've got better and better. And then we bounced against the law. In the UK, radio law has typically been quite suffocating for the experimenter. For me, as a license holder, to set up an unattended station, well, I was fine to do it because I have a full radio license, which used to be called the advanced radio license. But if someone who holds an intermediate, the second level of license, or a foundation wants to do it, they're not allowed to because they haven't sat the right exam. And while the exam says that you know the base amount about radio, it doesn't necessarily say you know how to remotely turn a computer off and on, and the licensing body were very concerned about people with computers. So laws exist to be bent, and we gave some people some good advice on just how to do things and what unattended operation could be interpreted loosely as, and how to experiment with things. And then we got the opportunity last year to change the laws. We started speaking to the body that coordinated all of the packet stations in the UK and highlighted some things that didn't make sense, and they reissued the allocation of frequencies. And then the radio regulator in the UK, Ofcom, came knocking and said they would like to change radio law because they really can't be bothered dealing with us as radio amateurs. So they made everything a lot more permissive. And now a foundation license holder in the UK can just pop up an unattended station. You can't use too much power, but can do it. And an intermediate license holder can put up a full power unattended station. And the network blossomed. As soon as we had freedom from regulation, it got much easier. And other people wanted to get involved too. So the network extends out to Gothenburg and Hamburg and the Netherlands now as well. And usually at night, my station will connect and we'll get messages from the continent. And of course, because I'm a Linux person, I came up with a stupid Linux problem, or a stupid Linux solution to a problem that didn't really exist. So the Raspberry Pi is popular, and we want lots of people to do packet radio, so surely we can bring the Raspberry Pi and the packet radio together. I also happen to maintain all of the packet radio infrastructure in Debian, and thus the Raspberry Pi. It trickles down. And Raspberry Pi OS trails Debian by about 6 months. And Debian, when we release stable, well, we've been in a freeze for about 6 months. So by the time that a Raspberry Pi gets something, it could be 12 months out of date at, in the best of situations. So there must be a way to get people newer software on Linux than just pulling it off the internet. So I came up with some ideas, and we'll get to where I ended up with that thought later. But what I did learn is that free software is just really hard for people. They're really scared to play with computers, and telling someone that they can nano edit this config file, vim edit this config file, is just not a valid option for a lot of the new people that we had joining our group. And we had to work out how to teach them how to do that. And it's compounded by the fact that the software is old and fiddly, and it's often just distributed as binaries by an author with no code behind it and no way of understanding how to engage with open communities. And then there's the documentation. Well, I said the websites are bad. Well, we tried our own documentation, and wikis, well, wikis are a great source of information, but people forget they exist and nobody ever reads a wiki. And we exist in Discord as a community, and Discord is horrible. It eats everything that you say, and it doesn't return it in a helpful manner when you search, and it doesn't put it on the open internet. And all of the conversations you have and discoveries you come up with and ideas and thoughts really should just be considered lost by the time they go into Discord. And the wheel keeps getting reinvented, and we keep coming up with the same ideas. And the people who are writing the software just want to write the software. They don't want to write documentation for the software, which is understandable. So I started to write a coherent guide, and people got excited about the packet radio guide, and then Linux Brain came on. And I invented Hibby's packet radio repo, which is an idea that brought a lot of work. So I thought I'd abuse my Debian hobby of building software for other people to build software for other people in a radio context. And my first response was, yeah, just copy repo.list to app sources list D and my GPG key to trusted gpg.d, which, to anyone who is not into command line, is the ramblings of an absolutely unhinged madman, and we had to rethink that quickly. So now there is a package that you install, and it sets up your computer, and I get permission to install whatever I want on your machine. And what I'm trying to do is backport software that is at the bleeding edge of where we are to older platforms, to Raspberry Pi old stable, to Raspberry Pi stable, Ubuntu, Debian. It's become about 7 operating systems across 4 different architectures. And then I ran into build systems are really hard, because doing that many things takes a lot of time. So I got into refining my build system, and it became a bunch of scripts, and then that became 25 scripts dressed up in a trench coat, pretending to be a Linux distribution that's now somehow called Hibbian because someone threatened violence if I didn't call it that. And then starting a Linux distribution has brought its own idiotic problems as well. Well, I have to have a website, and I have to have a mailing list, and I have to have a Git repo, obviously, and then that just keeps forking into ever smaller projects and ever smaller hobbies, and that seems to be my hobby, is just forking into more problems. So once people had software from my excellent repo that I spent far too much time on, we hit a new problem. And it is the social challenge of running a network. Keeping the network running depends on all of our participants being happy. And the network will root around interpersonal conflict. What happened at home was I went away for a long weekend, and the guys near me decided that my system was making the wrong noises, and they didn't want to play with me anymore. So they changed frequency, and no one thought to send me a text saying, your system's broken, can you just turn it off? So I got home, and everything was quiet in the house. And I have a speaker on all the time, and I can just hear the noises, because it's just 1200 and 2200 hertz audio. So I just hear little burps of packet going back and forwards, but the house was silent, and that's always worrying. So I went and looked at all the radios, and everything was wired up okay, so I unwired everything, and my radio room is a mess of wires, because there's 7 radios and 5 antennas and all sorts of stuff. And everything was wired up fine, so I wired it back together, turned it all on, and bumped a knob and changed channel and heard everyone else all of a sudden. And that's when I got upset. But rerouting the network does solve other problems. And we recently identified that we have a lot of interference on our shortwave channel, so our long-haul channel. The war in Ukraine has brought a lot of Russian interference on the amateur radio bands. And we found a quiet spot, and we have moved into that quiet spot, and we've applied some channels for different speeds and different networking technologies. And now our network is more interconnected than it was before. We have these reliable links up and down the country that work every day, and we have these links to different countries that work every day, and we can send messages to each other much more reliably now. So when the network roots and we manage the social challenge okay, everything works. And then to send mail, well, this is the mail forwarding screen in our preferred node package, our preferred BBS. As you can see, it's really simple. It's very obvious what's happening here. I am doing something. This is the caliber of software that we have to deal with. And really what I'm doing is sending bulletins to 71 to 78, which is the Scottish packet addressing scheme, to this guy in Glasgow, Michael, GM5AUG. And anyone that sends mail through me goes over my shortwave link to Glasgow. I have one to the Isle of Man. I have one to Reading. They go all around the country. And these are two-way agreements that we've made. We've agreed between us that I will send mail there and they'll send mail back. But these rules aren't set in stone. So there's a guy who is 2 hops down from me who doesn't like sending mail through me. He likes to go through his pal in Edinburgh. So the two of us are in competition to try and attract users from the local area. And it's always entertaining when we meet for a pint. But yeah, the network manually routes around problems. Unfortunately, given the age of some of our operators, occasionally someone dies, and we do have to route around that as well, which is a weird set of phone calls to have. So I came up with a Linux solution, and it was insane, but it turns out I can bring the insanity to FreeBSD as well. So if you want to join in the UK network from all around, well, on the modem side, so to create audio, well, you have soft modems like Direwolf and QT Sound Modem, which is a piece of software that's reasonably available, and the author does produce binaries for FreeBSD. And if you want hardware, well, there's the Nino TNC, which is a driver of what we're doing, and there's also now a plethora of units on LoRa and other technologies. You need a terminal to access it. You can't just use a regular terminal, and the most common is Qt-term TCP, and again, the author provides binaries for FreeBSD, which is nice. And he is also the author behind the main node stack, and the node stack handles all of the network connections, all of the routing, all of the bulletin board, and the live chats as well. And he released some binaries about 3 years ago for FreeBSD. And I spent a long time banging my head off the wall trying to get the code to build, and it didn't build, and it didn't build. And then last night, I cracked it at 5 past midnight. So the code now builds and runs on FreeBSD 14 AArch64 as of last night. The big problem I ran into was these wonderful if-in-defs FreeBSD, and the compiler didn't like them, so I just removed all of the code, and it built. If you need a computer, well, pick your favorite, find a weird computer and stick it on. Antennas, still not software, but you can build your own, and they're great fun. And yeah, for BPQ, Qt-term, and Qt Sound Modem, if anyone wants to help me get that into FreeBSD ports, I'd be really happy to get that into the wider BSD ecosystem, and we can have a more interesting and diverse network. And the picture at the top is my FreeBSD system last night in a hotel, just calling in and saying that I'm running the latest version. I did speak to the author previously about why it wasn't building on FreeBSD, but unfortunately someone had reported a CVE against his incomplete telnet implementation. So he was busy fixing that instead of talking to me about BSD. What's next for our network? Well, IP seems good. That's a technology that's going well. Radio amateurs have a lot of IP addresses. We had 44/8 for a long time, and then sold some of it to Amazon. So now we have 44/9 and 44/128/10, which is about 12.5 million IP addresses, and you can just ask for a /24 to do what you want with. The slow-speed links really don't lend themselves towards IP because they're slow, and IP is quite a lot of overhead, but 9600 does. It is implemented in the Linux kernel, and it will come as no surprise that it is an incredibly wonky implementation with lots of weirdness going on that no one understands. There's bugs that are outstanding for 10 years that no one wants to fix, but it is usable, and you can spend 5 to 10 whole minutes of your own time downloading a crap website in the clear, should you choose to. And of course, because it's no encryption, everything happens in the clear. Telnet, HTTP, no one's been brave enough for null cipher SSH yet, but I'm keen, I'm convinced it's allowed. And software is changing as well. All our software is aging and creaking. It is contemporary with when diskette care was something you really had to think about. Don't put them in the toaster. In 1998, radio amateurs produced a new version of the AX25 spec, version 2.2, which solves a lot of our sore points and pain points that are slowing networks down, and it is barely implemented. BPQ, the node stack that we use, implements it perfectly, but the Linux kernel stack doesn't, and the other implementations, it is unclear whether they do or not. And much of the software is now unmaintained. The Linux kernel has a lack of direct maintenance on the components that are in there, and really it doesn't have to be in the kernel at this point. It's not fast networking. The Linux kernel stack has been wobbly since kernel 3, which is quite a long time ago. It saw really big updates in 5.17, which was about 2 years ago, and it saw more updates 2 months ago in 6.9 that have been backported into 6.6, and still nobody trusts it. It's still not good. And the other problem we have with software maintenance is that the software authors are dying, because some of this stuff was written 40 years ago, 30 years ago, and unfortunately we all don't keep going on forever. And then the paradigms that we're networking with are inefficient and out of date by most modern standards. As I suggested earlier, Layer 2 has a full connection machine that handles requests for retransmissions and lots of other things, as opposed to like Quick's approach of UDP at the base layer that we have now. And if we put TCP and IP on top of that, then we have multiple things asking for multiple retransmissions all the time, and everything gets slow and sticky. And when you don't have much bandwidth, you don't want stuff to get slow and sticky. And then, well, why don't we just start again? Like, we have loads of people now that we can communicate to and push software to and enthuse into doing new things. But it's really easy to suggest a perfect solution to a problem when you have no intention of implementing it yourself. Someone tried, Ian in Aberdeen, MM0ROR, tried spinning off OpenBSD into HamBSD and implementing all of the AX25 in that, and ran out of steam after it turned out that no one would fund it, and it was quite a lot of work, and no one would collaborate, and no one really cared. But I really want to see him work on and finish HamBSD. It'd be great fun to have an OpenBSD appliance that I can just sit down, connect a serial device to, and speak to the rest of the world. Other people are doing this as well. It's not just in the UK. We're not just a weird little country that speaks to each other on the radio. There's a group in the US, or there's multiple groups in the US under a banner known as Tarpin, who use the same foundations that we do. They use the same BPQ node, so theoretically, we could squeeze FreeBSD and others in there as well. They have an installer that is a whole series of shell scripts that download each other and refer to other shell scripts that then download more. And it does seem a bit insane, but it is quite a nice web-based UI. It does live conversation. You get a map of the local area. It's quite nice. There's a system called WinLink, which is global email over HF. And it is largely the same as what we are doing. It's the same bulletin board protocol. It's just dressed up and advertised differently. It is widely believed to be illegal in the UK. Don't get caught doing radio crimes. It is very hard to get caught doing radio crimes, but I wouldn't recommend doing them in the first place. In the UK, our licensing situation is subtly different from our neighbours, and we are not allowed to pass messages that have originated from someone who is not a radio amateur. And that's why we believe that email is illegal. This is a discussion that is happening at the moment, and we'll see what comes out of it. There's an application called JS8 Call, which is store and forwards, always on text messaging, and it introduces the great innovation of TDMA, time division multiple access. The time slots on JS8 Call are 15 seconds long, and it whips along at 12 words a minute. But it is quite reliable, and it borrows its modulation from another protocol and technology called FT8. It's slow, but it is a really efficient use of the band space that we have on shortwave. And there's other networks as well that are leveraging packet. APRS is the most common. That's what my screenshot at the start of the map was. It's more like a chat app, direct messaging. It routes over the internet as well as over the air. And it doesn't care about who is where. It's just repeaters that blindly repeat a signal a couple of hops. It could be more like WhatsApp. It could be more like a chat app. Maybe that's what the kids today want instead of a BBS. I don't know. But yeah, these networks are fun to play with. And then there is also Meshtastic, which is really popular at the moment, and it doesn't require a radio license. It's happening on the license-free frequencies. And that is an experiment in passing messages and dynamic meshing with really cheap hardware that you can get off AliExpress. And there's going to be so many more people trying radio networking and data that I've not heard of that are just getting on with what they like to do. And then technology is changing and improving slowly. The Nino TNC that we use and the multi-mode digital voice modem, which is used to emulate DMR and Tetra, are introducing higher speeds in the narrow channels that we work in. So in our VHF medium-sized links, we can now do 9600 bauds, and in our 25 kilohertz wide UHF channels, we're now seeing 19.2 kilobit a second, which is unbelievably fast. And there's a rapid proliferation around the world of astonishingly cheap LoRa devices, partly through Meshtastic and partly through these just being turned out really quickly. And they are really small. This is one that I got for £15 off AliExpress, and it will send and receive data and messages just as well as the big HF radio will, but over a smaller area. And this is another one that's got inbuilt GPS. So when I'm climbing hills with all of my gear, it tells my partner where I am and if I'm dead or not. And they're small, they're cheap. This one enumerates as a Bluetooth modem, and I can just send data back and forward over it. And this one will appear on a wireless network as a serial modem that I can attach to and send data over. So they are much simpler to set up and use, and it's an all-in-one ESP32-based device. And we're seeing these appearing in our network, and it's really interesting. And then equipment's getting cheaper as well. This is a handheld that comes from China. It's a standard walkie-talkie size. And what's exciting about this is that the firmware has been reverse engineered, and there are new software implementations for the radio. And that means we can tinker with the settings that are inside it, and you can make the turnaround from it transmitting to not transmitting really fast, and use it, and with a couple of soldering board level modifications, do 9600 baud over a £15 radio, as opposed to the 250, 300 pound commercial radio that we had to do up until this year or last year. And then there's new modes. I keep telling people that you can do IP over DVB-S over the amateur radio geostationary satellite that is in orbit. The people that run the satellite don't like permanent infrastructure on it, so we can't always have it running, but it's nice to do broadband couple of megabit wide. There is a development ongoing at the moment called New Packet Radio that takes all of the old technology and throws it out and starts again from scratch, and is effectively a layer 2 bridge. And you attach an Ethernet cable at one end, an Ethernet cable at the other end, and it will handle everything in the middle. There is someone in the UK collaborating with a group in Germany on a new generation of hardware for that, and is being funded from the, I guess, sovereign fund that was gained from the sale of IP addresses to Amazon. And hopefully that will bring hundreds of kilobits up to megabits onto the bands that we're already using largely similar equipment. And then we could take the German approach and just put microwave point-to-point everywhere. Because in the continent, they have the Hamnet, and all it is off-the-shelf microwave gear, slightly detuned to be in the amateur bands. But I, for one, would quite like a return to full-blood TNC, modem, all the logic inside one box, and you just plug your radio into it, plug your dumb terminal into it, and everything's gone. And I think that OpenBSD would be a great target for that, which is why I want HamBSD to help. Here are some helpful links. If you want to get started, there is a Get Started guide at my personal Linux distribution. You can always ask me for help. You can email me. And then these ungainly links at the bottom are some software that will work on FreeBSD at the very least. Apart from Xrouter, you'll need Linux emulation in the middle. I'll put the slides on the program system so that you can download the PDF and click the link, as it's much easier than typing in John Wiseman's documents address. And hopefully, given time, you will join me in combining all of your hobbies and climbing to the top of a mountain in the Scottish Hills with a laptop and speaking to strangers via packet email on a different continent. And then it rains and the laptop gets ruined, and you can't bring it this weekend to play with packet radio in a field in Ireland. Thank you very much.
just for questions. Questions, if you take any.
Yeah, yeah. I can talk about radios all day. So there's been look at using it, but everyone's a bit scared of just implementing new things. So at the moment we're stuck in the old ways and we're busy reinventing the wheel instead of looking at standards and trying to implement them properly.
What are the legalities for licensed ham operators to reuse unlicensed band devices like Bluetooth long range 5 or
It's
Wi-Fi?
generally okay as long as you stay within the bands. At that point, it is operating under your license as opposed to the license or type rating that is given by the jurisdiction that had it originally.
Does that mean at that point you're allowed to add an amplifier to the output stage and input stage?
Yeah, as long as you're not interfering with other people then. So we have on the geostationary satellite, it's 2.4 gigahertz uplink, and people are running 10, 15 watt amplifiers off the back of essentially commercial Wi-Fi equipment together. Excellent.
Thank you very much.
Thank you.
a bunch of servers from Linux to our beloved family of operating systems. Welcome, Stefano.
Thank you, and let me start saying a big thank you to the organizers of the event for inviting me and giving me this great opportunity to tell you how and why I started this interesting operation of migrating most of our servers and our client servers from Linux to the BSDs. Even if the operation might sound challenging, I can tell you it's quite rewarding. So I'm glad to be here and tell you how things are going from this side. Let me start by introducing myself. I am Stefano Marinelli. I solve problems. I'm the founder and current barista of the BSD Cafe, which is an online community of BSD enthusiasts and people who want to join a community to share knowledge in a safe, relaxed, and quite friendly way. So please join the BSD Cafe if you want to join a place like that. And I work in my company called Prodotto in Rete, which is a very small company which is focused on creating solutions for clients, creating solutions to solve problems. So not selling boxes, not selling hype solutions. We're just creating what the client needs, what we need, and what we believe in too. So this is Prodotto in Rete. I am passionate about technology and computing. I've always been, so it was natural for me to make my passion my profession. So this way, I wake up every morning with a smile on my face saying, what am I going to discover today? That's the best thing that you can do when you wake up and have to go to the job. So let's start with the early days with Linux. I started here with this. I had no broadband connection. I was just 16 years old at that time. I was joining the FidoNet network and was reading about those open source Unix-like operating systems. And I was quite curious to try them, but I had no way to obtain one of those operating systems. So I found this CD box and I bought it, and I tried that all the distributions that were present, so Red Hat, Debian, and I loved that kind of approach, the Unix approach, the Unix way of simplicity, of combining pieces. I loved the pipes. It was love at first sight. And, but at that time, my computer wasn't powerful enough to dual boot, so I had to revert to Windows because I was 16, I wanted to play games. So I had to wait 1 year. As soon as I had a more powerful computer, I have been able to dual boot. And I realized that Linux could become my daily driver, keeping Windows only for those things that I could not use on Linux, like Win modems or scanner or gaming. But I had no further necessity because I could cover all the necessity I had with Linux. So I was quite happy about that. And this was great because in 1998 I started university in Bologna, Italy. And that computer science department was completely oriented towards open source solutions. And not many were aware of this kind of solution at those times. So I was one of the few students already able to, let's not say manage, but to run a Unix-like system. And I already knew the open source concept. So I was quite happy because I could use at university all those things that I had learned just trying Linux and working with Linux at home. In the year 2000, I was lucky enough to have Professor Ozal Babaoglu as my teacher. And while he never made pride of his work at Berkeley, all the students were chatting. Do you know he's one of the founders, of the creators of the BSD operating system? I wasn't aware at all of the BSD system. So I started studying this kind of system, just reading some of the documentation I could find. But I had no broadband connection and not a powerful enough system to keep Windows, Linux, and one of the BSDs. So I had to wait the year 2002, when I had a new computer. It was a Sony Vaio laptop, and a broadband connection. At that time, I started exploring all the BSD systems. Unfortunately, OpenBSD wasn't working at all on my laptop, but FreeBSD was working, and NetBSD was working, mostly working, let's say. At the time, I became one of the administrators of the Underlab. It was called Underlab, the laboratory of the university where students could use those PCs, and it was completely Linux-based at that time, and was selected for managing a project for the university called FreeOS Zoo. The FreeOS Zoo was a collection of ready-to-use operating system images that people could download from the website. It was a wiki, actually. I created a wiki, and run inside their computers. And the project was quite successful. And sometimes the creators of the operating systems sent me the images, the operating system virtualized images, like Andy Tannenbaum sent me Minix, for example. And this was absolutely great. But at that time, I wanted to go deeper with the BSDs. So in 2002, I convinced my parents that I absolutely needed a laser printer because I needed to print university stuff. Of course, the first thing I have been printing with that printer has been the FreeBSD handbook. But, you know, I never used it for my university topics, but it's OK. And so I started to print everything I could find about the BSDs. I still have tons of paper, 22 years old, so maybe a bit yellow, with all the BSD documentation of that time. And FreeBSD became my daily driver because it was running much, much better than Linux on my laptop. It was snappier, it was more stable. I had no problems at all. The problem was that I was young. I loved personalizing stuff, so I wanted to recompile everything, the base system and all the packages. So I remember entire nights spent with my laptop 1 meter away from my ears, with spinning wheels like crazy because I was recompiling KDE, and it was an operation 20 hours long, more or less. So in 2003, I was finishing my university graduating, and I decided to make a final thesis about open source virtualization solutions, which at that time were quite immature, let's say, on the Linux front. There was QEMU, but it was just, I don't think it reached the beta at that time. It was just an alpha. And one of the most interesting solutions I found and decided to use was Xen NetBSD. It was stable, it was reliable, it was working for all the tests I've been doing at that time. So that was the surprise. I decided to show my teachers not a Linux solution, but a BSD solution. And they appreciated it, so I was quite happy. At that point, I started to search for a job, of course. And I started working for a company offering Linux-based solutions. But the problem was that it was OK for me to use Linux, you know, open source operating system. At that time, there was a nice philosophy behind it, so it was OK for me. But the problem was that those Linux systems were just running, not breaking, not giving problems, no blue screens of death. So my boss was complaining that those Linux servers were hurting the company billings. So he was asking me to create some less stable servers, less stable services, because he needed clients calling and asking for repairments. I was disappointed and sad because, as I told you at the beginning, I solve problems, and IT is my passion. I cannot do something I do not believe in. I cannot do something I would not use myself. So at that time, I was also teaching some Linux basics to some non-Linux IT administrators. And one of them suggested me to open a business, a one-person business at that time, and try to sell the services or consultancy following my rules, not the rules of a boss that wanted me to make something I would not believe in. So at that point, I was reasoning about it, and I decided I was young enough to try it, but following my own guidelines. And those guidelines have been set more or less 20 years ago, and I'm still following them with slight variations. from that time. Make your own kind of music. I will never listen to others saying, you have to use this. No, I'm going to experiment and decide what I want to use for my servers, my clients, my data. This is the basic idea that I had 20 years ago and I still have today. So the base of my philosophy is I solve problems. I don't sell boxes. I've never sold boxes. Maybe a client could ask to buy a router or a firewall, an external device. It's OK. I'm going to do this. I'm going to configure this if it's OK for me. But I will never sell boxes. You will never see me with a branded shirt of a specific brand, a specific vendor, and providing those solutions only. It would never be. So I would work for myself, following my philosophy. OK, I told you already. I would use and promote open source solutions. I believe in open source. I think that the open source is the key for democratic IT, because everyone can take a piece of software, deploy it, test it, use it without having to spend tons of money in licenses or other strange things like consultancies. And whenever possible, open source had to be used. And according to my experience, maybe not long at that time, but still enough to make me decide, I would use BSD, one of the BSD, of course, anytime I could. In case it was not possible, Linux would be good enough. So I started, and things initially went quite fine. But the problem was convincing the clients that the open source solutions were serious business solutions, solutions that could be applied on production servers, even out of university. They were just dismissing anything, saying, oh, those are just toys for universities. The real world runs other kinds of software, and they usually meant Windows. Windows was out of my philosophy completely, and still is. So some of them accepted Linux just as a test. I also proposed I will do all the setup without asking you a single euro. The day you will be convinced and you will see how much you have saved from the license cost, we will decide how much you are going to pay me. It was risky, but it worked. So the clients accepted this kind of approach, while tended to reject the BSDs, because they had never heard of them, so they were not going to make a jump so wide. So I decided to use the BSDs for my own infrastructures, so for providing services to clients, and not where clients were involved in installing or using those systems, or at least where clients were rejecting that solution. So NetBSD XAN, as stated, for virtualization, and it was a great platform. One of the most appreciated and still linked articles of my blogs, on my blog, is the article about that old NetBSD server running unattended for over 10 years. One of those servers have been running for over 10 years. It's mine, yeah.
You are that guy.
Yeah, I'm that guy. And it's been running for more than 10 years without any kind of intervention. A client called me one day saying, could you please modify the network interface there? Are you still running that? Yes, of course, it's perfect. On consumer-grade hardware. So NetBSD XAN was a great combination at those times. Maybe it's still today, but I'm not using it anymore. OpenBSD as network firewall entry points. When something had to be exposed, I was going to expose OpenBSD as much as possible. And FreeBSD, especially when ZFS came in, for various services, including backup servers. I'm still using FreeBSD for all my backup servers. Sometimes I'm using Proxmox backup server for my Proxmox servers. And I'm running Proxmox backup server inside a Beehive virtual machine on a NetBSD host. I'm not putting Proxmox on bare metal, Proxmox backup server. So that was the initial situation. And clients were quite happy of those setups. Clients were happy about the stability, the reduced need for maintenance. They were doing their job without any interruption for, hey, this panicked, oh, this is broken, oh, I need to run to. All the maintenance windows I was suggesting were respected. When I said, I will stop 2 hours your services for an upgrade, generally speaking, after 1 hour, they were back online because the BSD systems are reliable and predictable. They will not change anything from one release to another. But the problem arose. If everything's working, what am I paying you for? And that was a great problem at that time, because they were used to systems that were breaking, and security wasn't as a hot topic like it is today. So they were just saying, maybe we could stop paying you because we don't need you anymore. And many of them did that. So I decided to choose the clients that understood that the most important thing isn't how many times I'm going to put my hands on that machine, but how much that machine will be stable and run with the correct maintenance, of course. I'm not going to abandon it until the next disk will break. Preventing problems is much better, in my own opinion, of course, than fixing problems. I solve problems. So this is still a part of I solve problems. After some years, Linux started to gain popularity. And that was great, because open source solutions were getting more and more attention and more respect, considering that some years before they were just toys. The problem was that the clients started to ask for Linux, specifically for Linux, also those who had working BSD setups. And that was sad for me, but you know, clients were asking something I could deal, so better accomplish the mission than lose the client if they wanted Linux at all costs. So I started to remove those excellent NetBSD Xen servers and implement solutions based on Linux, like at that time it was OpenNebula, or some early versions of Proxmox. So they had some graphical user interfaces that they loved to use, and I can understand it. For non-tech people, it's much easier to connect to a web interface and click reboot of a virtual machine than connect via SSH and use Beehive, VM, restart. You know, for me, it's the opposite thing, but you know, we're tech people. So I was happy because those solutions were not considered a toy anymore. Fast forward, let's go on. After some years of this new setup, I found out that no BSD has ever caused me to lose any data requiring a restore from a backup. And it's still, maybe tomorrow everything will explode, but in this specific moment, it's been more than 22 years, I've never lost a bit using a BSD. Any of the BSDs, ZFS, UFS, all the BSD file system, FreeBSD, NetBSD, OpenBSD, not a single bit. While all the most adopted Linux file systems cause me some headaches, let's say just headaches. More than one X4 file system suddenly exploded, no problems on the disks, no problems on the virtualization platform. They just started spitting errors and weren't mountable anymore. Searching on the net, I found many problems like those. XFS caused me a small data loss. It was a client who had big files, so XFS at the time was suggested for those kinds of workloads that were recovered by the backup, but the client wasn't happy anymore. So that was a very bad experience. And recently, I lost a Butterfly system. Recently means 5-6 years ago. A 50 terabytes Butterfly system on Linux. Just a RAID setup, not RAID 5, RAID 6. RAID 1, just a mirroring setup, because RAID 5, RAID 6 have problems on that Butterfly system. A reboot caused an unpredictable error, and nothing could be mounted anymore. But the client was good enough. That was just a backup server, because I would never put anything in production on Butterfly system. So I asked the client, can I remake the whole setup on ZFS and FreeBSD? They said, yes, go on, please. And we never lost a bit since that day with the same device, the same disks that caused this problem with Butterfly system. And another important thing about the BSD's setup, I tend to create read-only when possible, or better, when needed, read-only root file systems. And FreeBSD has native support for it. because sometimes you will have to leave devices unattended where power isn't reliable or you cannot put a UPS. We're talking about small companies, offices. We're not talking about big tech companies. My clients aren't big tech companies. My clients are small web agencies or some e-commerce websites or just some healthcare institutes. But maybe they have to put a specific device and you can't control the whole power line. But having the read-only root file system assures that, unless there's a problem with the root disk, you will always be able to get back inside the system and mount the other file systems or check them without having to physically go to the client and connect via serial port or HDMI or whatever. So this was one of the first things that I noticed in time. And I started noticing some industry trends. And you know, hypes are driving the market everywhere. So I started by request in 2018 to introduce Docker to some devs that had specific needs. And it was a good tool because they needed to create specific setups that were quite glued together, and it was quite difficult for me to follow them. But the problem is that in time I found out that many of them are using those Docker setups just to create something I would never put online for them. I would never do. 10 days ago, a dev just asked me to put online a new Docker server because they need to create a PHP 5.5 based application. I will never allow this to go online under my management. So that was one of the points, but of course, it's not related to Linux. But it's related to the trend. The development of Linux and distribution is starting to fade out from the original philosophy of the Unix, keep it simple and stupid, do one thing, do it well. But it's going to most complex and bloated, let's say bloated solutions. I'm not against systemd. It's OK, systemd, but I don't need systemd. Why should you give me systemd at all costs? So I'm just trying to stay away from all those solutions that have more lines of code than the rest of the operating system itself. Because sometimes today we have the tendency to replace the old with the new just for the sake of doing it, not for solving problems, specific problems, but just for the sake of, hey, there's a new way, let's all do that way. No, that's not part of my philosophy, because I think that there is no one-size-fits-all. I study solutions for clients, and I prefer to provide clients solutions and not the hypes. So let's go on. New technologies should solve old problems, not create new problems worse than the ones they were supposed to be solving. And common people don't care at all about the solution you've used to create that kind of setup. They want their website to run, to be reachable, to be secure, to be stable, to be fast enough to cope with the spikes, but they don't care if it's running on Docker, on a FreeBSD jail, or OpenBSD. So the point is, there is no single solution to all problems, like many say today, but there are many solutions to one problem. And my job is to give clients the best solution, not the most fashionable one. So at a certain point, I got fed up of this, and I decided to revert my percentage. In 2011, 2012, I'd say, 65% of the workloads I was managing were BSD-based, and 35 were Linux-based. There has been a moment at that point, the proportion had reversed, but in a terrible way, 70% Linux, 30% BSDs. So I decided it was time to get back to the BSDs. And I decided that was my way to solve problems, to solve their problems. So the goal was to create a stable, coherent, upgradable, and secure systems. Provide those to clients, propose them to clients, or just don't tell clients what I'm using. If they just need an email address, they don't care if there's Linux or Illumos or a BSD. They just need to click connect and check their emails. So I started exploring, again, the advantages of the BSD systems and proposing to clients. So what I'm saying to clients, OpenBSD needs minimal additional packages. The base system is complete. So many of the workloads they have to cope with are already covered by the OpenBSD base system. And the OpenBSD base system is secure by default. NetBSD can run for years with a few updates. It's happening that some clients are worried because they still have some production machines, not exposed, of course, on i386 architecture. And FreeBSD is steering away, Linux is ceasing the support. NetBSD will continue to support, as much as possible, all the old architecture. Sometimes those kinds of machines can't be replaced easily because they're production machines. So NetBSD is appreciated in those kinds of situations. And FreeBSD, thanks to ZFS, Beehive, Jails, is my favorite choice nowadays for an all-rounder system. So if you need to create an hypervisor, if you need to create a jail-based setup, FreeBSD is the operating system I'm going with. So I decided to start migrating everything I could. This was around 2020, 2020, late 2019, early 2020. So at first I decided to migrate all the systems that needed upgrades, always causing problems because I was starting from the problematic ones to see how things were going to perform. And to have a better understanding of the situation, I just leased actually, some twin machines, some machines that were identical hardware-wise to the ones that were in production. So I could replicate the setup on FreeBSD or other BSDs and see the performance, the stability, everything that could happen there. And what I noticed immediately, moving machines from Linux virtualization platforms like Proxmox or others, and FreeBSD, Beehive-based VMs, was an increase in I/O performance, and of course, lower resource usage, because, yeah, FreeBSD with Beehive is just basic FreeBSD and the Beehive process. There's no all the web interface or everything else. And Beehive is great performance-wise. I've also written a blog post about it. I've done some comparisons last summer. And Beehive is great with I/O. So both using the virtIO driver, even better with NVMe driver, Beehive is great for those workloads. So I started to make a real-world test. I didn't tell anything to the client. I could do that by contract, so I was perfectly fine. I'm recorded, so I must say that. And I started migrating some of the virtual machines the client was using on some Linux servers to the FreeBSD hypervisor. Over a weekend, I migrated some virtual machines without saying anything to the client. On Tuesday morning, I received a phone call from the client. And the client was terribly worried because they noticed an increase in performance. And they were worried that I had upgraded the hardware and of the costs. This will cost us too much. Why did you do that? Actually, that was the very same hardware involved. So I explained to the client what was going on. And the client decided to go on with this kind of migration. And we continued. The client was quite happy. So we went on with that client and others and tried to modify the setups. Many of their virtual machines were actually just web servers or mail servers or Java applications running with Tomcat. So there was no reason to run a virtual machine for that. So I started to move those workloads to FreeBSD jails. Generally speaking, in FreeBSD native jails. In some cases, I had to use the Linux emulator to replicate the Linux setups, just moving with rsync, and everything worked. So that was great. Living in two virtual machines, just those solutions that I could not migrate completely, like some Zimbra mail servers or other packages that I could not touch. And this led to a massive performance increase, because not depending on virtual machines meant native I/O speed, because jails are still writing directly on the ZFS datasets, and no double buffering, because we're not buffering on the host and on the VM. So this led to a huge save of RAM. So starting from then, the client has been able to reduce from 20 physical hosts to 11. The client is happy. He's saving money. The services are stable, are more performant than before. The client is quite happy. And now they just want BSD-based solutions. So that was the first success of this migration. So I continued with this and started involving the devs. The most difficult part at this point, because devs are used to say, Docker Compose up, my workload is up. I started to introduce the jails, the advantages of having the raw data. And they could access those data, automatic snapshots with ZFS, so when they were doing a mess, they could revert without telling anyone. And they started to appreciate the kind of setup. Of course, I prepared some template jails, so they could clone them in just a few seconds and configure according to their needs. And many of them were quite happy, so they started requesting new jails and FreeBSD hosts instead of Linux hosts. So that's been quite interesting. And more about it, younger devs are not used to profiling their software. They just say, oh, this website is slow, let's power up the server. Let's just turn on the auto-scaling. And this led to many problems I've also described on my blog. So those young devs understood the importance of checking what they were gluing together. And they were, especially the ones who are passionate, they immediately understood the importance to have those kinds of solutions and go on that way. So the problem is often ideological, not technical. I can say that for almost all my workloads, there's no need to run Linux. And I'm much better, I sleep much better when I have the BSDs under my servers. The clients are often influenced by the hypes. I remember 20 years ago, Linux is a toy. Then, why are you using Proxmox? Why not VMware? Today, they're saying, why Beehive and not Proxmox? Maybe I'm just a generation, you know. And so, how can they sell FreeBSD? There's no AI, there's no cloud, there's no Kubernetes, there's no blockchain, there's nothing of that inside these BSDs. So I'm just trying to convince them that we have to return to simpler solutions we can manage, upgrade. Sometimes they say, we need to upgrade that, but it's such a mess that we cannot touch it, otherwise everything will explode. This will never happen with a BSD, unless you're really messing them a lot. And so I'm also convincing them to be always the owners of their data. They always need to be the real owners of the data. The data should be where they can get them. The data should always be in a form they can export, re-import, modify, transform. But that's the most important thing that I'm trying to advocate to those people. Never be locked in inside a solution, because entering is easy, getting out is impossible. So the BSDs are easier to maintain, so why we are migrating? Because it's easier for us to maintain BSD servers. And they run better, actually. My first-hand experience is that. Of course, each of us has his own experience, and they have a few layers. There are not too many layers. The jails are inside the FreeBSD kernel. There are not pieces just glued together to keep the, the privileges down. We are just doing these ways. And one example is the recent OpenBSD of Theseus. Every file of the OpenBSD original source code have been touched, but still we have OpenBSD and it's still the same OpenBSD. So it's been evolving, but it's not been changing just for the sake of changing. So this time I solve problems by not overcomplicating solutions. I try to solve clients' problems providing simple solutions. Sounds strange nowadays, but that's what happens. And clients notice because, you know, so updates or reboots won't cause problems. A rebooted BSD system will generally reboot. This happened recently to me. I rebooted a Proxmox server, and the main network interface has been renamed from that to that. No, I want that this stays this. I had a Proxmox server that started to give problems because at reboot, the ZFS module, external module in Linux, of course, wasn't working. So all the pools with the virtual machines were unmountable. I have FreeBSD ready with ZFS native. It will always mount a ZFS dataset unless it's broken. And NetBSD, because the architecture, your architecture, will be supported and tested. So you can be sure that someone is taking care of your architecture. You're not going to have legacy software, even if you have legacy hardware. And this is great. So the devs, I already introduced this slide, but actually the devs are asking for jails. Yesterday, the last request has been, I need some more jails of that kind. It was a dev that 6 months ago was asking for Docker hosts. And I'm glad that this person has converted to the BSDs. They learn to manage the resource, and I don't hear that much, we need more power, when something goes wrong. So that's the point. The final client is happy because the services are stable. I'm trying to advocate to avoid the monocultures because relying on a single operating system is bad, even if a single BSD. Because a problem on that operating system could lead to a disaster. I'm not referring to CrowdStrike, but you know. And value the stability and security of the BSD systems. When the recent SSH vulnerability has become public, many of the clients called me saying, we need to run to upgrade our servers, they're in danger. And many of them were quite happy when I said, no, your SSH server is on OpenBSD, so that patch has been fixed in 2001, even before I was aware of OpenBSD itself. And the reply I got was, why aren't we doing more OpenBSD servers then?
Good question.
Exactly. Exactly. Better this than what are we paying for? So this was the client situation. But the problem now in embracing an BSD-only setups often is the problem with the managers. The managers sometimes sell things they don't understand at all. They just try to sell products, they try to sell solutions, and they are quite in a difficult position when they cannot mix the words Linux, cloud, Kubernetes, AI, blockchain, cryptocurrencies, whatever. So they ask me, how can I sell a solution based on a BSD when my final client doesn't even know about BSD, where Linux is everywhere? And this is a problem I'm trying to face, as I told you before, just trying to highlight the advantages of running the BSDs instead of Linux. Not because Linux is bad, but because the BSDs are better, at least for those workloads. And another problem I'm facing today is the compliance problem. They call me and say, what's the version of this SSH we are running? Oh, it's the last of OpenBSD. No, we need to have this one, Debian. I said, no, we're not running Debian. It can be that. Oh, sorry, but we have to comply with that. And that's a problem, because sometimes they ask me to take the responsibility that I take when it's a matter of keeping the BSDs, that release is, in that specific day, more secure than this one. And I'm quite sure that it is. And the problem is that the people who prepare those documents, compliance, are often totally unaware of what they're asking for. So people controlling those things aren't absolutely unaware of that. So the BSDs aren't a part of their checklist, and I'm fighting because I want the BSDs to be a part of that checklist, because they cannot ignore those great operating systems. And I would never install something that I would not use myself. All my precious data is on the BSDs. Nothing is more on Linux of my own precious data. So how are things going with this transaction? Quite well, I must say. Yesterday, but today it's the same as I didn't touch anything, 78% of hypervisors I manage, so not only my hypervisors, but clients' ones as well, are running on FreeBSD. And they just run. Every time I have to, I just upgrade FreeBSD, I reboot the virtual machines, everything comes up perfectly. And 66% of the workloads of any kind I'm managing are running on BSD systems, FreeBSD mainly, but also OpenBSD, NetBSD. I'm doing some tests with Dragonfly BSD for HAMR 2, which I really consider interesting, but I have no workloads in production with that. The clients love moving from those shiny, expensive boxes produced by those big players of the firewall routing to OpenSense solutions. I just say, just have a try and let me know what you think. And I don't hear from them anymore. I try to ask them, how are things going? If I don't call you, it means it's perfect. Great. And developers love FreeBSD jails, as I said before. So, which are the next steps? Now I want to start migrating my clients from the big email tech to self-hosted solutions. I'm moving in that direction, calmly, but it's working. The point is, I've seen problems between Gmail and Outlook users of false positives of spam. So if you're using a good IP, both in v4 and v6, and you're keeping all the DNS records updated and make sure that good emails, people won't spam using your servers, things will eventually go in the proper way. I've been self-hosting my emails since 2001 and never had to rely on an external server or provider, and never had big problems. Of course, the false positive marked as spam happens, but happens also with big players. So I'm planning to launch, at last, the BSD mail service that I've been announcing on the socials for months, but there's some problems, bureaucratic mainly, where all the MTAs will be OpenBSD-based with OpenSMTPD, and behind Dovecot, RSpamD, SOGO in jails, replicated using Dovecot replication, MySQL master replication for users, SOGO connected to the same Redis replicated using KDB. So I want to provide BSD mail service to give clients the possibility to have their emails stored on encrypted at rest ZFS datasets, not in control of societies that want to check their emails for business purposes. Continue to explain people that they have to avoid being trapped in lock-in solutions. They have to be free. They want to I want clients to choose our services because they believe in us, not because they're forced to. So they have their data. In case they want to go away, they just take their data and go away. Because I don't want to work with people that do not want to work with me. And this is one of the first parts of the philosophy. Go over 90% adoption rate for my BSD adoption. So client servers, our servers are all on BSDs, but client servers as well. And things are improving quite fast. And continue to document many of the solutions I'm solving using the BSDs on my blog, because I found out that many people reading my blog contact me saying, I moved from Linux to the BSD systems because I found your post. I knew how to do it because of your enthusiasm. And I think that this is one of the key parts. People should be aware of what we have here, and we are the ones that have the duty to teach them, to show them, and make them free to choose what they want to work with. So, final thoughts. The transition to the BSDs is going smoothly. Clients are satisfied, appreciate everything we're doing. We are satisfied. The phones are not ringing at night with disasters or notifications, or much less using the BSDs. We will continue to be committed to providing best solutions, BSD-based, but not only, because I want to believe in what I'm offering my clients. No hypes, no shiny boxes, just solutions for clients. So, to sum up, I'm Stefano Marinelli. I solve problems, and I love solving problems using one of the BSD. Thank you.
That's a little present from us for you.
Thank you.
We
Much
don't have
appreciated.
time for questions here, but you'll be at the social event, right?
Yes, I will.
So we'll do the questions and answers over beer.
All right. That's okay for me.
That's the end of this day. I hope to see most of you at the social event, and again, tomorrow.
Just one last thing. Let me say just last thing. Thank you all for listening to my story. Thank you to my wife, which supported me to come here and encouraged me to meet you all. Thanks to Florian, Azim, Hoberg, Giptesi for reviewing my slides. And again, thank you to the organizers for this great event. Thank you. And I'm waiting for you all at the BSD Cafe, by the way. Hi.